Hey everyone, hope you're doing well today. In this video, we're going to be taking a look at reviewing Algebra 2 together. Real quick before we get started, if you'd like to download a free copy of this blank PDF or look at some of the other annotated answer keys or other resources that I have to offer, you can find a link to that below. Not only will you find some materials for Algebra 2, but you also find some stuff from 6th grade all the way up to calculus as well. To get the most out of this video, I encourage you to grab some paper, something to write with, and let's do some math together. In number 1, we're going to go ahead and write an equation of a linear line that passes through the points -4, 12, and 3, -2 in slope-intercept form, standard form, and point-slope form. I'm going to start with point-slope form first, so the equation is going to be y minus y1 is going to be equal to m, or the slope, multiplied by x minus x1. All right, now we can use either one of these points, but I think I'm just going to go ahead and use the 3, -2 because they have smaller numbers. So that's going to be our x1 and y1. So we're going to have y minus -2 or plus 2 is going to be equal to m, which we don't know quite yet, is going to be multiplied by x minus 3. All right, so using the point that we had there. Now to figure out the slope here, let's go ahead and do that on the side. So remember, slope is going to be equal to, now for the vertical change here, we have 12 minus -2 or 12 plus 2. That's going to be the rise. The run's going to be -4 minus 3. That's going to be the run, or the horizontal change. Simplifying this a bit, we're going to have 14 over -7, which means that our slope here is going to be -2. All right, so that's going to be what our m value is. So writing our equation in point-slope form, we're going to have y plus 2 is going to be equal to -2 multiplied by the quantity of x minus 3. This would be our equation in point-slope form. Next, let's go ahead and write this equation in slope-intercept form. And to do that, we can just take our point-slope form here and rearrange it a bit. So let's go ahead and distribute this -2 to both of these terms inside of this parentheses. So if we do that, we're going to get this y plus 2 is going to be equal to -2x plus 6. And then if we go ahead and take away 2 from both sides, we're going to get y is equal to -2x plus 4. This would be our equation in slope-intercept form. All right, finally for standard form, it's typically easiest to just go ahead from slope-intercept form. So standard form, we have ax plus by is equal to c. So if we go ahead and add 2x to both sides of this equation, we're going to get this equation of 2x plus y is equal to +4. Now for this particular equation, that's all the work that we had to do. Just keep in mind that when we're writing this in standard form, our a value, or the 2, has to be a positive leading coefficient, which we already have here. Now feel free to check this if you want, but if you go ahead and take all 3 of these equations and graph them, or throw them into a graphing calculator or something like Desmos, you'll see that all 3 of the lines lie on top of each other and go through these 2 given points. All right, here is number 2. In number 2, if y varies directly with x and y is equal to 12 when x is equal to 4, find y when x equals -5. Now the key bit of information in the problem that we need to pay attention to is that y and x vary directly with each other, so that means they are proportional through multiplication. So we're going to say y is equal to k, which is just a coefficient or constant, multiplied by x. As opposed to if it says varies indirectly, it would be something like y is equal to k divided by x, which would be an inverse relationship. So that's not what we have here. Okay, so we start off with this general form for direct variation, and they tell us that y is going to be 12 when x is equaling 4. So for this particular case, we can say that we have this point of x comma y, which in this case, they're telling us we have this point of 4 comma 12, right? So let's go ahead and substitute those values in. For y, we're going to say 12 is equal to, and that's k multiplied by 4. Okay, if we divide both sides by 4, we know that k's value is going to be equal to 3. So the general form for this direct variation relationship is going to be y is equal to 3x. All right, that's our direct variation equation, which is really just a linear equation that goes through the origin, if you want to think about it that way. Now, while this isn't the answer, it's the general equation that we're going to use for this relationship. So we're going to go ahead and use this to find out y when x is equal to -5. So let's go ahead and plug that in. We're going to say find y when x is -5. So it's going to be y is equal to 3 multiplied by -5 here. So we're just making a substitution in to see what this hypothetical value would be. So we're plugging that in right over here. And if x was equal to -5, then y would be equal to -15. So basically we just found out here that if x was -5, then y would be -15. This would be a point that would be on this line as well. This right here would be the solution. All right, let's check out number 3. In number 3, it says to describe the transformations compared to the parent function and state the domain and range of the function in interval notation. All right, so notice that we have an absolute value equation. We have f of x is equal to 3 times the absolute value of this x minus 1 expression minus 4. So in order to know what the transformations are, we need to know what the parent function is. The parent function is just going to be f of x is equal to the absolute value of x. Now, if it's helpful, we can take a look at a general form for the equation to help us with the transformations. This is going to be common with some other types of functions as well, so this hopefully will be helpful. So the general thing we can think about here is if we have a general equation of y is equal to a, that's going to be kind of in front of our absolute value symbol, multiplied by this absolute value of x minus h, and then that is going to be then adding k on afterwards. Just a real quick review, this h lets us know what type of horizontal translations we have for the function, mainly the vertex to kind of start. This k is going to let us know what kind of vertical translations we're going to have up or down for the whole function as well as that vertex. This a is going to let us know if it's positive, it's going to be having a minimum. If it's negative, it's going to reflect it across the x-axis, then it's going to have a maximum instead, as well as it's going to let us know if we have a vertical stretch or shrink, or I guess some people also call it a compression. So looking at these specific variables here, if we look at our function, we're going to go ahead and identify each of these pieces here. So we know right away that a in this particular case is going to be equal to this positive 3, so no reflection, but we do have a vertical stretch. In this case, we know that h is going to be equal to positive 1, so that means we're going to have a horizontal translation of 1 to the right, and then k here is going to be equal to negative 4, so we have a vertical translation down 4 units. So writing this out a little bit more clearly, since a is equal to 3, we know we have a vertical stretch by a factor of 3. Because h is equal to 1, we have a horizontal translation of right 1 unit. And because k is equal to negative 4, we have a vertical translation of down 4 units. Let's just go ahead and take a look at this on Desmos real quick so you can see a visual. So here's the parent function that we were just talking about, and if we want to go ahead and find the function or see what it looks like that we were given this particular problem, let's go ahead and see. We have this 3 multiplied by the absolute value, we have this x and then minus 1. So notice it's already a little stretched than it was before because of that 3. Notice how the vertex moved to the right 1 unit because of that minus 1 we just put in. And then outside here, if we put a minus 4, notice that the vertex actually is moving down. So that h comma k lets us know that the new vertex, at least the vertex for this particular function, is 1 to the right and 4 down. Notice how the slope of the lines are also going to be 3 times steeper than usual. So the slope is going up by 3 on the right side of this absolute value function, and it's having a negative slope on the left side as the function is decreasing. So this is going to be all the transformations we just applied. Now, as for the domain of this function, keep in mind that's all the possible x values that we can have for this particular function. So I don't see any reason why the function is going to be stopping as we go to the left forever. So this absolute value function is going to move to the left forever, approaching negative infinity, put a parentheses there, and it's going to, as we go to the right, approach positive infinity. So that's going to go to the left and to the right for infinite distance. Now the domain are all the possible x values for this function. Now we looked at that graph, it wasn't going to stop going to the left forever, and it was never going to stop going to the right. So in both directions, it's going to go towards negative infinity to the left, positive infinity to the right, and make sure you put parentheses around the infinities because we use brackets if it's inclusive. Now, while the domain lets us know as we're moving left to right, the range is going to let us know our limitations or our bounds as we're moving down to up. So keep in mind that this absolute value function did have a minimum. Its minimum y value was at negative 4, and it did exist at negative 4, so it's inclusive. So let's put a bracket on negative 4. But the function did go up infinitely, so it's approaching positive infinity as you go upwards. This would be the domain and range for this particular function. Let's try one more problem dealing with linear functions here. So in this particular problem, we have something dealing with a linear inequality instead. So this is our original linear inequality. Let's go ahead and rewrite this into slope-intercept form so it's a little bit easier to work with. Right now it's in standard form. It's a little bit trickier to visualize. So taking away 3x from both sides of the inequality, we're going to have negative y on the left side is going to be less than negative 3x minus 2 on the right side. Then if we go ahead and divide both sides by negative 1, we're going to end up with a positive 1y on the left side. Keep in mind, if you multiply or divide both sides by a negative value, then we're going to flip the less than symbol to a greater than symbol. And if we're dividing everything on the right side by negative 1, we're just writing the opposite. So we're going to have is greater than 3x plus 2. Now in your head, if you want to think about this as y is equal to 3x plus 2, feel free to do so, because if you know how to graph this, that's going to help you kind of get started with graphing our linear inequality instead. All right, so keep in mind that this plus 2 means that we have a y-intercept of 2. So if we go ahead and plot that on the graph here, I'm going to put that at this 2 if we're saying every box is worth 1 unit. Now our slope is going to be 3, so we're going to go up 3 over to the right 1, up 3 over to the right 1 as well. You can also go down 3 and to the left 1 because it's the same ratio. Down 3 to the left 1, down 3 to the left 1. All right, so this would be letting us know where the path of this line is going to be. Now, if this was an equation, we would go ahead and keep this as a solid line. Also, if we had a line underneath here, this would also mean that we would have a solid line, but keep in mind that the y value has to be greater than 3x plus 2. So we're going to use a dashed line because none of the points that are on this line are going to satisfy the inequality. It has to be either above or below the line to be a solution. Not only do we have to decide whether we have a dotted line or a solid line, but we also have to decide which side to shade of this line because either all the solutions are going to be underneath the line over here, all of these would be solutions, or if those aren't the solutions, then everything on this side of the line would be a solution. So it's either or. Generally, what we do to test this is we test a point. So if we test this point over here of 0, 0, that's a nice easy point. That's at the origin. If we test this point and it does make the inequality true, then all of the dots on that side, all the coordinates over there would be solutions. So if we substitute this in, it would say 0 is perhaps greater than, let's put a question mark there because we're not sure yet, 3 multiplied by 0. Again, we're plugging in 0, 0 in for x and y. And we're going to see if this is true or not. So we're going to have 0, is that possibly greater than 2, right? So is that true? Well, it's not true. So that means we know we're not going to be shading that side of the line. So that means any coordinate that's on the other side of this line would be a solution. So anything over here, and feel free to test a few points if you would like to, but we can say some solutions that would be a solution versus a non-solution. So if you wanted to test out a couple solutions, feel free to do so, but a point like over here would totally work. That's going to be the point -1, comma, it looks like that's going to be +5, so that would be a solution. You could also say something like over here, which would be -9, comma, 0. So as long as you pick a point where we shaded, those would be solutions. All right, now as for some non-solutions, maybe something like down here, this would be 0, comma, -8. That would be a point that's on the other side that's not a solution. Or something like over here where we say 10, comma, 2. This would also be a non-solution. These 2 points would not work because they're not on the side that's shaded. All right, so there you have 4 different practice problems dealing with some linear relationships. Let's take a look at some linear systems now in part 2. All right, so in number 5, we have a system of linear equations with 2 variables here. Now to use elimination, we're going to go ahead and try to make some matching coefficients here. You can either make these coefficients for the x's match or be opposites, or make these match or be opposites. Either one is okay. I think in my case here, I'm going to go ahead and make the coefficients for x match here. So I'm going to go ahead and multiply this whole top equation by 2 because then we're going to have matching coefficients of 4. We're going to leave the bottom one alone or just multiply it by 1. However you want to think about that is okay. So the goal is to get matching coefficients or opposites. If they're opposites, we're just going to add them together afterwards. If they're the same, we're going to subtract. So the top equation is going to be 4x plus 10y is equal to 16. And the bottom equation is just going to stay the same because the identity property of multiplication, anything times 1 just stays the same. Or you can think about just not doing anything, that's fine too. So let's go ahead and subtract these 2 equations from each other. So 4x take away 4x, that's going to be eliminated, hence the name elimination. So that's going to be eliminated. Then we have this 10y, take away the 3y, so that's going to be 7y. And then finally we have 16 take away -12, so that's become 16 plus 12, that's going to be 28. We can go ahead and divide both sides by 7 and say y is equal to +4. Okay, so that's going to be at least that's going to be the y coordinate of our solution. Let's go ahead and see if we can find out the x coordinate. So let's go ahead and take this y is equal to 4. Let's go ahead and just substitute that in. You can choose either equation. For me, I'm going to go ahead and just substitute into the top equation because it looks like there's just less negatives and some smaller numbers there. All right, so substituting that in, it's going to be 2 multiplied by x plus 5 multiplied by 4 is equal to 8. And so if we go ahead and simplify this a bit, we have 2x plus 20 is equal to 8. If we take away 20 from both sides, we're going to get 2x is equal to -12. And dividing both sides by 2, we're going to get x is equal to -6. So now that we have x and we also have y, we have the coordinates for the solution for the system. So if we were to graph these 2 linear lines, they're going to intersect each other at -6, comma, +4. So that would be the coordinates of where they cross each other. This would be our solution. Now, keep in mind that you don't always have a solution for a system of linear equations. Sometimes if the lines are going to be parallel to each other, it's going to have no solution, or if the lines are actually the same exact line, you could have infinite solutions because the lines lie right on top of each other, so every point on the one line is also a point on the other line. All right, let's check out number 6. In number 6, we're going to go ahead and solve a system, but this time we're going to use substitution. Now, just so you know, it's generally going to be more useful or friendly to use substitution when one of the variables already has a coefficient of 1, because we can kind of isolate one of those variables much easier. So it's up to you. In this particular case, it looks like x or y could both be isolated pretty easily, so it's totally up to you. So I think I'm going to just do is I'm going to isolate x. If I isolate x here, then we're going to go ahead and take away y from both sides. So x is going to be equal to negative y minus 6, right? So if we're just turning that around and taking that x and isolating it by itself. And what we're going to do is just make a substitution into the top equation. So notice where this x is right over here. We're going to say 2 multiplied by whatever x is. We just said x is the same thing as negative y minus 6, right? The same value, okay? Minus 3y is equal to negative 2. All right, so now the equation only has one variable, so it's something that we can solve. So we're just using that second equation to substitute in. So let's go ahead and distribute this 2 to both of these terms. Distributing that, we're going to get negative 2y minus 12 minus this 3y is going to be equal to negative 2. Let's go ahead and combine some like terms. We're going to get negative 5y is going to be minusing 12, and that's going to equal this negative 2. If we add 12 to both sides, we're going to get negative 5y is equal to 10. And dividing both sides by negative 5, y is going to be equal to negative 2. All right, so this is going to be the y coordinate of our solution. If we go ahead and take this and just substitute it back into one of our equations, we can solve for x. So I'm going to go ahead and just substitute into the bottom equation. I think that one's a little easier. If we do that, we're going to have this x plus negative 2, or just x minus 2, is going to be equal to negative 6. And then if we add 2 to both sides, we're going to x is equal to negative 4. So this would be the x coordinate for our solution. So putting this together, the coordinates at which these two lines will intersect each other are going to be at negative 4 comma negative 2. This would be our solution for this system. Let's take a look at number 7. All right, number 7 looks like we have a system of linear inequalities. So keep in mind with inequalities, we don't generally just have one solution. We're going to have possibly infinite solutions here, right? So that could possibly happen here, especially because we're talking about shaded regions. So it is possible that the shaded regions don't overlap, so we could have no solution, but we'll see what's going to happen here. So let's take a look. Let's take a look at this system. I think what we're going to do, and it says graph them, is we just have to literally put this on a graph, but I'll show you where the solutions and where the non-solutions are going to be. Let's just take a look at one equation at a time here. So for this top equation, let me just go ahead and rewrite this into slope-intercept form, just so it's going to be a little bit easier to graph. So if we go ahead and do that, this first equation, we have 2x plus 3y is going to be greater than 6. If we take away 2x from both sides, we're going to get 3y is going to be greater than negative 2x plus 6. And if we divide both sides by 3, we're going to get y is greater than negative 2/3 x, and then plus 2. All right, so that's going to be our first equation that's in kind of this slope-intercept form. That'll help us with the graph a bit. And then our second one is this 2x minus y is less than or equal to 8. So let's go ahead and take that equation and rearrange it as well. We have 2x minus y is less than or equal to 8. Let's go ahead and take away 2x from both sides. We have negative y is less than or equal to negative 2x plus 8. And if we go ahead and divide both sides by negative 1, keep in mind we're going to flip the inequality, and then we're going to have is greater than or equal to 2x minus 8. So these would be our two inequalities written in slope-intercept form. All right, let's go ahead and throw this on a graph so we can see where the solutions are going to be. So for that first inequality, our y-intercept is going to be at 2. Our slope is going to be negative 2/3. So let's go down 2 and to the right 3, down 2 to the right 3. Or we can go up 2 to the left 3, up 2 to the left 3. And we should have enough points to draw a line. Now ask yourself, should we have a solid line or dashed line? And if you said dashed line, then you are absolutely correct. Now we have to decide what side to shade. I'm going to test 0, 0 into our inequality. So here's 0, 0 below the line. If we plug in 0 here for y as well as 0 in here for x, this whole thing is going to become 0, and it would just say 0 is greater than 2, which is certainly not true. So the areas that would be solutions for this single linear inequality, at least this one by itself, would be all the points on this side of the line. Now let's take a look at our other inequality. So our y-intercept here is going to be at -8, which is down here. Our slope is +2, so you can go up 2 and to the right 1 to get some points that would be along this line. Now go ahead and ask yourself if we should have a solid line or dashed line in this particular line. Now, if you said solid line, you are absolutely correct because we have this inclusive line underneath. It says that any point along this line would be a solution as well. Now, what about which side we're shading? Let's go ahead and test 0, 0, which is right over here. If this works, we're going to shade this side of the yellow line. So try to ignore that purple line for a little bit. If we plug in 0, 0 over here, it would just become 0 is going to be greater than or equal to -8, and 0 is bigger than -8. So we're going to shade, I guess we could say technically above this line here. So anything that is on this side of the yellow line would be a solution. Okay, so anything over here. Now, if you're wondering what types of coordinates would be solutions for the whole system, anything that's in the area that got double shaded, which would be anything in this space here. It can't be on the dotted purple line, but it can be on the solid yellow line. That is okay. Anything that is over here in this particular purple area, it works for the purple inequality, but not the yellow one. Anything that's over here does work for the yellow one, but not the purple one. And any coordinates that are down here would be points that don't satisfy either one of them. So that would be an area that doesn't work at all. All right, let's go ahead and try one more type of system. In this one, we have a system, but we have 3 variables instead of 2. For these particular problems, I generally just like labeling our different types of equations. So I'm going to call this equation A, equation B, and equation C. That's just going to help us organize, which one I'm talking about when I'm talking about them. Now, when dealing with these 3 equations and 3 variables, our goal is going to be to eliminate a variable and get 2 equations with 2 variables. So what I'm going to do first is I'm going to go ahead and see if I can get all of these y terms to have the same coefficient. So in order to do that, I think I'm going to make them all 3. So 3 or -3 at least, right? So I'm going to multiply the top one by 3. This middle equation B, I'm just going to go ahead and multiply by 1 or keep it the same. For equation C, I'm going to go ahead and multiply this one by 3 as well. So look what's going to happen here. So for equation A, we're going to have 6x plus 3y plus 9z is equal to 15. For the second equation, nothing's going to change. We're going to have -x plus 3y plus 1z is equal to -14. And then for our equation C, it's going to be rewritten as 9x minus 3y minus 6z is equal to 33. All right, so here's our new equation A, B, and C. Now, if we go ahead and use the fact that they all have the same or opposite coefficient for that y term, we can go ahead and eliminate the y's and write 2 new equations here. So let's actually re-highlight that third one. I'm just going to go ahead and re-highlight this equation C term so we have that negative, right? So let's go ahead and start with going ahead and taking equation A and taking away equation B. That's going to eliminate the y's, right? So if we go ahead and do that, then if we do A minus B, it's going to be 6x minus this -x, so that becomes 7x, right? If we're going ahead and subtracting them. Then if we take this 3y and take away this 3y, they're going to get eliminated, okay, which is good. Then this 9z take away 1z is going to be 8z, so we have 7x plus 8z. And then finally for the constant, we have 15 take away this -14, or 15 plus 14, that's going to be 29. So this is going to be a new equation for us after we take b away from a. All right, now I'm going to go ahead and take equation B, and this is up to you which one you do, but I'm going to take equation B and add equation C. And you're going to see why I'm doing this in just a moment. I'm doing an addition here because these are opposites. One's plus and one minus. If one's plus and one's minus, we want to add them to eliminate them. So going ahead and adding this equation B and C together, if we have -x plus this 9x, that's going to be 8x. Let's go ahead and write that down here. We have 8x. Then we take this 3y plus this -3y, they're going to eliminate, which is good. We have this 1z plus this -6z, that's 1 minus 6, or it's going to be minus 5z. And then finally, we have this negative 14. We're going to go plus this 33. So it's really 33 minus 14, and that's going to be 19. So it's going to write 19 over here. All right. So we have these two new equations here. Just to stay organized, let's call this equation D, and let's call this equation E. And let's also just make them a different color to stay a little bit more organized. All right, so this system here should look pretty familiar because we solved one similar in number 5 and number 6. Now, if you're wondering between elimination or substitution, I wouldn't use substitution because it's not easy to get any of these variables isolated. They all have different coefficients, so only use substitution if you can get x or y, alone pretty quickly. I think we're just going to go ahead and use elimination here. Now, you can choose to either eliminate the x's, but 7 and 8 meet at 56 for the first time, or eliminate the z's, and 5 and 8 meet at 40 for the first time. It's really a preference thing, but I think meeting at 40 is a little bit easier in my head. So I'm going to go ahead and multiply the top equation by 5, and I'm going to multiply the bottom equation by 8, just so I can get matching coefficients for the z terms. Okay, so if we go ahead and do that, I think we're going to get 35x plus 40z is equal to 145. That's just our new equation D. And then we're going to have 64x minus 40z, and that's going to be equal to whatever 19 times 8 is. I think that's 152. Okay. And so we're going to take these two equations here and notice how we have opposite coefficients. So if they're opposite coefficients, let's go ahead and add these equations so they eliminate. So this 35x plus 64x, that's going to be 99x. It's going to put 99x here. Go ahead and add this 40z plus negative 40z, those eliminate. And then we take this 145, and if we go ahead and add that onto this 152, that's going to be 297. All right. Now, if we go ahead and take this equation, divide both sides by 99, hopefully you see that x would equal 3 here. All right, so after all that work, we have one variable, we have x. We still have to find out y and z. Now, don't go ahead and plug this thing back into one of these 3 original ones yet because there's too many unknowns. However, you can go ahead and plug in this x equals 3 into either equation D or E to find out the value of z. So I'm gonna go ahead and do that right now. So let's go ahead and take this 3 and substitute it in for this value of x right here to solve for z. So substituting in, we have 7 times 3 plus this 8z is equal to 29. 7 times 3 is 21, so we have 21 plus 8z is equal to 29. If we take away 21 from both sides, we say 8z is equal to 8. Divide both sides by 8, so z is equal to positive 1. So that's going to be another part of our solution. All right, so now that we have that z is equal to 1 here, let's go ahead and take this z is equal to 1 and pick one of those equations in the very beginning that we can go ahead and plug this into. I'm going to go ahead and plug it into equation B just because z is by itself. But we also have to go ahead and take this x equals 3 and plug that in as well. So let's go ahead and take this x equals 3 that we got earlier and plug that in into this equation as well right over here, and then we can solve for y. So let's go ahead and do that. If we go ahead and plug that in, we're going to get negative 3. Negative 3 plus 3y. We don't know y, so we're going to leave that alone. Plus z. We know z is equal to 1. This is equal to negative 14. Okay, so let's combine negative 3 plus 1 is negative 2. So we have 3y minus 2 is equal to negative 14. Let's go ahead and add 2 to both sides. We get 3y is equal to negative 12. And then if we go ahead and divide both sides by 3, we're going to get y is equal to negative 4. This right here would be the last missing piece for the coordinate that we were looking for this system solution. So we can go ahead and write our solution as kind of like this ordered triplet maybe. So where you have this x goes first, and then our y is going to go second, and then our z is going to go third. So not an ordered pair, but I'm calling it an ordered triplet. And so we're going to have this as our solution. Now feel free to check it. You can plug these 3 values in for x, y, and z into this first equation A, or equation B, or equation C, and all 3 of them should give you true statements. All right, so that wraps up part 2 of this review. Let's move on to part 3, where we're going to work on quadratic functions a bit. All right, so let's move on to part 3, where we're going to take a look at some quadratic functions. In number 9, it says to describe the transformations compared to the parent function of f of x is equal to 2 times the quantity of x plus 4 times the quantity of x minus 2. Then state the intervals of which the function is increasing, decreasing, positive, negative, and the domain and range. All right, so we have this function here, and if you look closely, you can notice that it is a quadratic function. So that means the parent function is going to be x squared. So this is just a parabola. So we're going to see what kind of transformations happen to this parabola to get the one that we have in this particular problem. All right, so here's the function that we were originally given. It's in factored form. It's going to be a little bit easier to see the transformations if we rewrite this into vertex form. All right, so I'm going to go ahead and multiply this out. So I'm going to have x times -2, 4 times x, and 4 times -2. This way we can turn this into standard form. So we have 2 times the quantity of this x squared, the minus 2x plus 4x combined to make a plus 2x. And then the 4 times -2 we said was -8 here, so that's going to be this. Next, we could distribute that 2 to turn this into standard form, but we can see the transformations a little bit more clearly if we have this whole thing in vertex form. So to have this in vertex form, what we're going to do is I'm actually not going to distribute the 2 to the x squared or the 2x. I'm actually just going to distribute this 2 to the -8 and take it outside of the parentheses. So watch this. We're going to take this 2. I'm going to keep this x squared and plus 2x, keep that inside the parentheses here. I'm going to leave an empty bit of space here, but I'm going to distribute the 2 to the -8 and write -16, right? So if we went ahead and just distribute this 2 to both of these terms, we would get what we have above, right? As long as you were to distribute out that 2. But we're going to go ahead and complete the square on the inside here. So to complete the square, remember we take half of the b term, so half of 2 is going to be 1. We're going to square that, so that's going to be 1. So we're going to go ahead and add 1 in here. And so we add 1 inside the parentheses. Keep in mind that we're technically adding 2 because there's this 2 on the outside, so just doubling everything that's inside the parentheses. So if we want to keep this whole thing balanced and not just create this extra +1 or really +2 into the problem, let's go ahead and make sure we balance it out by putting a -2 here. All right. And if this feels a little weird, go ahead and pause the video and go ahead and just distribute this 2 out to all of these terms here. Notice you'll get a +2, and then the +2 and the -2 will cancel out, so it's as if it wasn't even there. All right. So that's kind of how completing the square works, just so we can manipulate the problem and make it into a form that's a little bit easier for us. So here we have a perfect square trinomial, so we should be able to factor this into the quantity of x plus 1 squared. That was the whole point of completing the square. And then this -16 minus 2 is going to be -18. All right, so right now it is in vertex form, so we can kind of tell a few different things here. To refresh your memory, vertex form is in this a times this x minus h squared plus k, so it's kind of like that absolute value function that we looked at earlier. And if we know some values of these of a, h, and k, that can help us out with the types of transformations here. So let's see what are the types of values that we have. We have a is equal to 2, so that just lets us know that we have a vertical stretch. We also have this h is equal to -1, so we're translating this left 1 unit. And then we also have this k is equal to -18, so we're translating this down 18 units. All right, so for the transformations, we can say that we're going to have a vertical stretch. Okay, if you want to write, you can say by a factor of 2 or times 2. We can also say here that we're going to translate this thing left 1 unit, and then we can also say we're going to be translating this down 18 units. All right, so those are those transformations. All right, so moving forward now, keep in mind that this hk, what that represents, it's the vertex for this parabola or this quadratic function. So our h value and k value are going to be -1 and -18, so that lets us know what our vertex is going to be, right? And that's going to be helpful in just a moment as we write some intervals down. So I'm going to go ahead and write the vertex is at -1, -18. Now, because the value of a is positive, we know that this parabola is going to have a minimum and it's going to open upward. So we know the parabola is going to look something along the lines of this, and it's going to have a minimum value here at the bottom, right? It's going to open up because we have a positive a value. Now, let's see, when is this going to be increasing? Well, we know the parabola is going to be decreasing until it hits the minimum, then it's going to start increasing. So what x value does it start increasing at? It's going to start increasing at -1, or right after it rather. So at -1, it's neither increasing nor decreasing. So it's going to be increasing from this point of -1. Put a parentheses at the -1, and it's going to keep increasing forever after that, right? So if you look here, this is going to be at -1, and then it's going to keep increasing forever. Now, what about decreasing? Well, it would be decreasing as you keep moving to the right, all the way up until x is -1. So it's going to be decreasing from -infinity up until -1. At -1, it's again neither going to be increasing nor decreasing. Now, to figure out when this parabola is going to be positive or negative, we're going to need a little bit more information. So keep in mind what the intercepts are in this problem, right? So it's very, very important. If we take a look at our zeros, we take a look inside here, we can see that our zeros are going to be at x equals -4 and at x equal +2. Those are going to be the two x-intercepts. So if we go ahead and look at what our parabola would look like, we could see at least a rough sketch here that at -4 and at +2, we would have our x-intercept. So if we wanted a rough sketch of our graph, it would look something like this, okay, where our vertex is down here, and we have our two x-intercepts of -4 and +2. So you can see here that our function is going to be positive up until x is -4, then the function is going to be negative or below the x-axis up until x is +2, then after x is +2, the function is going to be positive again, or above the x-axis. So when is this function going to be positive? Well, it's going to be positive from -infinity up until -4, right? That's going to be this section here from -infinity up until -4. It's going to take a break for a moment. That's going to restart being positive after 2. So we're going to put this u for union, and from 2 up to +infinity, it's going to be positive again. So when is it negative? Well, it's going to be negative in between the x values of -4 and +2. So I'm going to go ahead and say that the negative interval of this parabola is going to be from -4 to +2. And keep in mind that at -4 and at +2, the function is neither positive nor negative because it's at 0. Those are the x-intercepts. Now, what about the domain? Well, the domain for all quadratics is going to be from -infinity to +infinity, right? There's nothing limiting the parabola from going left or right forever. So what about the range? Well, the range doesn't go down forever. It's limited to the minimum. So the minimum here is at -18. So we're going to go ahead and put a bracket because the parabola does exist at -18, right? That's a point along the graph. However, nothing is stopping this parabola from going up forever, right? So in terms of the range, the y values aren't limited at all, but they are just limited on the bottom because we have a minimum. So this would be the range. All right, let's take a look at number 10 now. In number 10, where it says to rewrite the function in vertex form, graph it, and state the intervals of the domain and range. Okay, so right now we're in standard form. We actually just practiced turning a function into vertex form a little bit in the last one, so hopefully that helped. But if it was still a little confusing, hopefully I can clear that up a little bit more now. So what I'm going to do first is take this function of f of x, and what I'm going to do is what I did just a moment ago is take this x squared minus 8x, the term with a and b, and then I'm going to just separate and then put this plus 13 over here, right? It doesn't really change the problem. I'm just grouping it a little differently. If you drop these parentheses, everything goes back to normal with what you see above. And then we do something called completing the square. So if that's a little bit fuzzy, what you do is you take the b term, which is -8, you take half of it, which is -4, and you square it, and we get this number of 16, and that completes the square, or turns this into a perfect square trinomial, right? Now, in this case, we're adding 16 to the problem, and there's an invisible 1 in front here, so we're really adding just 1 16 inside here, so we're going to take away 16 out here to balance out the fact that we just put a random plus 16 in here. So earlier we did something a little bit different because there was a 2, and that 2 kind of affected it a little bit more, so this one's actually a little bit more straightforward, hopefully. And so what we do here is, since we completed the square, this turns into, and I'll write this out a little bit more explicitly than I did in the last one, but it turns into x minus 4 when you factor it, and then 13 minus 16 is going to be -3 or -3. And then I'll just go ahead and condense this to show you that it does turn into that perfect square, or the quantity of x minus 4 squared minus 3. So this right here is our function in vertex form, so we can see what the vertex is going to be. So the vertex, again, is kind of being told to us by these values from here, the h and the k. So the vertex, I'm just going to write it down since it's helpful to know when we're doing the intervals. The vertex is going to be at 4, -3. Okay, that's going to be the vertex here. All right, that being said, when we're going to go ahead and write the domain is going to be all the potential x values that we could have for this function. So in interval notation, keep in mind for parabolas, it's going to go from -infinity to +infinity. As for the range, this is for the y values or the f of x values. This is the possible y values from the lowest point to the highest point. So in this case, we have a parabola. We do have a minimum of -3. We know it's a minimum because a's value is positive, so it's going to be opening up. So the lowest point of this parabola is going to be at -3. Put a bracket there because it's allowed to be -3. And it's going to be going up forever since there's no limitation on the positive side or the increasing direction. All right, here is number 11. All right, for number 11, we're going to go ahead and find the zeros of the function, which is really just another way of saying find the x-intercepts. The first thing you would try to do generally is going to be factoring. If you go ahead and try factoring, though, you're going to find that it's not factorable. The next thing you generally try to do is solve by square roots or complete the square. If you are fuzzy on any of those strategies, feel free to check out some of those resources I have in my library. But you're going to notice that completing the square isn't really friendly when you have an odd coefficient, especially in the beginning, that 5 there, especially if we don't have any greatest common factor that we could pull out from all three terms, so it's just not the most friendly. So in this case, when you see this type where it's not going to be factorable after you've tried and thought about all those methods, then the quadratic formula is going to be your best bet there. All right, so I'm going to go ahead and find the zeros using the quadratic formula. And again, like, I'm not saying don't try those other methods. You really should give those a go to see if one of those is easier. But the quadratic formula will work as well to find the zeros, especially if you're not sure. So it's going to be the opposite of b, so it's -2 plus or minus the square root of, and then we have b squared, so that's going to be 2 squared, that's going to be 4, minus 4ac, so it's going to be 4 times 5 times 5. This is going to be all on top of 2a, or 2 times 5, so that's going to be 10. So let's go ahead and clean up the radical a little bit. So we have this -2 plus or minus the square root of, and it's going to be 4 minus what? Well, 5 times 5 times 4, that's 25 times 4, it's 100. So 4 minus 100 is going to be -96, and that's going to be all over 10. Okay, so let's see if we can simplify this radical a little bit here. It's a -96, so we know actually that this is going to have complex roots, which makes sense. We weren't going to be able to factor this or solve it any other way, really, at this point. So if you want to remember how to simplify radicals, I'm just going to show you real quick. If you take the square root of -96, keep in mind that if we have a negative, we can take this as a square root of -1, which is I, multiplied by, and you need to think of some perfect squares that might go into 96. So I'm thinking it's going to be 16 times 6, that's going to be 96. So the square root of -1 is going to be I, and square root of 16 is 4, so it's going to be 4I root 6. All right, so if we go ahead and rewrite this, x is going to equal -2 plus or minus this 4I root 6, that's that simplified version of the square root of -96. This is all over 10. Notice how we have some common factors. We can divide everything by 2. So if we divide everything by 2, we have -1 plus or minus 2I root 6 all over 5. So writing our two complex solutions separately, we're going to say x is -1 plus this 2I root 6 over 5. We can say x is equal to -1 minus 2I root 6 all over 5. These would be our two complex zeros. All right, for number 12, let's go ahead and see if we can write a quadratic function whose graph has the given characteristics. The vertex here is going to be -3, -2. So when we know that the h value is going to be -3 and the k value is -2 if we're using vertex form. And it says it's going to pass through 1, -10, so that's an x value and a y value. So if we're given the vertex, we might as well go straight to vertex form. So I'm going to go ahead and write f of x and just kind of write that skeleton out. It's a times the quantity of this x minus h squared plus k. Okay. We can also rewrite this as y equals maybe this instead. So I'm just going to go ahead and copy and paste this here. So we have y is equal to this right over here. And we can go ahead and maybe make some substitutions in. So we know a y value. We know it's going to be -10. We also know an a value. Nope, we don't know an a value, so I'm going to leave that alone for now. We know an x value of 1, okay, minus h, so it's -3, so it's going to be +3. It's going to be squared, and then plus k, but k is -2, so we can write plus -2 or just -2. All right, so 1 plus 3 is going to be 4, so I can say -10 is equal to a multiplied by 4 squared minus 2. Simplifying this a bit, we can say this is -10 is equal to 4 squared is 16 times a, so 16a minus 2. We can add 2 to both sides. We're going to get -8 is equal to 16a. Then divide both sides by 16, so we get a is equal to -1/2. Okay, so now we know everything we need to know. So our quadratic function here is going to be f of x, or y equals, and then our a value is -1/2. multiplied by the quantity of this x. And then what did we say it was going to be plus 3, right? That's that h value. It's minus negative 3 or plus 3 squared. And then because we had a vertex going down 2, we have a minus 2 over here. This right here would be a quadratic function that passes through that 1 comma negative 10 point and has the vertex of negative 3 comma negative 2. All right, let's see what else we got here. Let's take a look at part 4, where we're going to take a look at some polynomial functions together. In number 13, if k is a constant, what is the value of k such that the polynomial k squared times x cubed minus 6kx plus 9 is divisible by x minus 1? Alright, so keep in mind that when they say it's divisible, that means that when you divide the two polynomials that you would get a remainder of 0. And if that's true, if we take a look at this x minus 1, right, if it's divisible by this, then we got to remember that x equals 1 would then create a 0 here. That being said, if it's divisible, that means this is a binomial that would be a factor. And that means that if x was equal to 1, then the y value of this polynomial would be equal to 0, or that x equals 1 would be an x-intercept. So if we know that to be true, then we can go ahead and say that if we take this k squared and we go ahead and multiply that by 1 to the third power, and then subtract 6 multiplied by k multiplied by 1, right, because we're replacing x with 1, and we add 9, that this has to equal 0. Cleaning this up a little bit, if we cube 1, that's going to be 1. 1k squared is just going to be k squared. If we go ahead and multiply the 1 times that minus 6k, it's going to be minus 6k plus 9, and that's going to equal 0. Now this right here is a pretty nice trinomial. It's actually a perfect square trinomial. You can go ahead and factor into this binomial of k minus 3 times k minus 3, or k minus 3 squared, and this would be equal to 0. So when would this be true? The only times it would be true is if the inside of the parentheses or that binomial is equal to 0, so k would have to equal 3 for that to be true. Now I just want to show you how this is going to work in case it's still a little confusing. If we take this k is equal to 3 and substitute it back in, we can go ahead and say that's going to be 3 raised to the second power multiplied by x cubed minus 6 multiplied by this 3, then multiplied by x plus 9. If we go ahead and write this polynomial out, 3 squared is going to be 9, so this would be what, 9x cubed minus 18x plus 9, and that would be that polynomial. Now if you go ahead and divide this polynomial right over here by this binomial right over here, we're not going to have a remainder. So you can go ahead and use either polynomial long division or synthetic division to go ahead and prove that. And so I'm not going to go ahead and do that right now. If you divide this by that x minus 1, you're not going to have a remainder. Okay, it's going to go in evenly. But I'll go over some synthetic division and some polynomial long division in a future problem. All right, in number 14, let's go ahead and expand the polynomial using Pascal's triangle. So this is a classic example where we can use Pascal's triangle since we have a binomial raised to a specific power. So I'm just going to go ahead and write out Pascal's triangle on the side here. So you always just start with a 1, and then you go ahead and write these 1s on the outside here. Then you go ahead and sum the two 1s to get 2, and then you're going to put 1s on the outside. And then I'm going to go ahead and sum the 1 and 2 to get 3, the 2 and 1 to get 3, and then put 1s along the outside here. Then I'm going to sum 1 and 3 to get 4, 3 and 3 to get 6, 3 and 1 to get 4. I'm going to put 1s on the outside as well. This is going to be our binomial raised to the 0th power, to the 1st power, 2nd power, 3rd power, 4th power. So I have to go ahead and do this one more time. So 1 plus 4 is going to be 5, 4 plus 6 is 10, 6 plus 4 is 10, 1 plus 4 is going to be 5. And again, we're going to have these 1s on the outside here. So this row right here is going to be helpful for us as we use Pascal's triangle to go ahead and factor, or I guess multiply out this binomial a little bit quicker. Now I'm just going to go ahead and lay this out the way that you typically might see it, so that's a little bit more clear. So if we have something like a plus b raised to the 5th power, we can go ahead and use a and b and just use each of these values from Pascal's triangle as coefficients. Okay. So what I mean is that this a is really representing this x here. So I'll actually go ahead and write that a is representing x. And then we can see this b here is really representing this 2y. So I'm going to say this b is equal to 2y. Right? So if we were dealing with just a's and b's, because this is a little bit easier, then if we know we're raising this whole thing to the 5th power, you could FOIL this out 5 times, or we can know that from Pascal's triangle, these would be each of the coefficients, right? So if we were just using the a's and b's, let's actually go ahead and change the color here. And so what we would do here is we would go ahead and use the coefficients from Pascal's triangle of 1, 5, 10, 10, 5, and 1. Then what we do is we take our a value and then we're going to raise it to the 5th power and then raise our b value to the 0th power. So b to the 0th is just going to be 1, so I'm not going to write it. And then we're going to go ahead and lose an exponent from, or lose a power from the a, so it's a to the 4th power. We're going to gain an exponent from the b, so it's b to the 1st power. Okay. After that, we're going to go ahead and go down one more degree for a, so it's a to the 3rd power, but b is going to gain a degree. So each of these terms are 5th degree terms. So it's a cubed times b squared plus, and then we're going to go ahead and lose another degree for a, but we're going to gain a degree for b. So a squared but b cubed, and then plus, and then we're going to do this again where we get a to the 1st power and then b to the 4th power. They're going to write plus here, and then we're going to have a to the 0th power, which is just 1, I'm not going to write it, and we have b to the 5th power. So if we were just kind of filling these in with a's and b's, this is what we would do. And let's go ahead and just make some substitutions now. So we know a is the same thing as x, so every time we see a, we're just going to substitute in x. And then for b, we know b is really 2y, so every time we see b, we're going to go ahead and substitute in 2y. Okay, so this should be a lot faster than foiling, just because we have the skeleton out. You just need to know your power rules a little bit here. Okay, so if we're going to go ahead and write this out, in this case we have, let's see, 1 times this x to the 5th power is just going to be x to the 5th power, and it's going to be plus 5, and then it's going to be x to the 4th power times b. Well, b is going to be 2y, so we're going to multiply this by 2y. Plus we have this 10 multiplied by a cubed, that's going to be x cubed. And if we go ahead and take this 2y and we square it, that's going to end up being 4y squared. Make sure you square the 2 and the y. And then after that, we're going to go ahead and say we're going to add 10 times a squared. A is x, so it's going to be x squared times b cubed. Now if you cube the 2y, 2 cubed is going to be 8, so it's times 8. And then the y cubed is going to be y cubed. And then we're going to add on this 5 times what? 5 times a, which is x, and then b to the 4th power. Now 2y to the 4th power, 2 to the 4th power is 16. So it's going to be multiplied by 16 here. I'm going to just carry it over. So it's times 16 and then y to the 4th power. And then we're going to go ahead and write plus 1 times b to the 5th power. Now b is 2y again, so 2 to the 5th power is going to be 32. And then y to the 5th power is just going to be y to the 5th power. All right, so if we go ahead and clean this up a little bit, this x to the 5th power is just going to stay the same here. We can't really do much there. For this term of 5x to the 4th power times 2y, 5 times 2 is 10, so we're going to have plus 10x to the 4th power times y. Plus, if we look at this next term, 10 times 4 is going to be 40, so we're going to say plus 40x to the 3rd power y squared. Plus, if we take this 10x squared times 8y cubed, 10 times 8 is going to be 80, so it's going to be plus 80x squared y to the 3rd power. Then we have this 5x multiplied by 16y to the 4th power, so 5 times 16 is going to be 80. So we have 80 times x times y to the 4th power. And then we have this last term of plus 32y to the 5th power, which we can't actually simplify at all. So I'm just going to write plus 32y to the 5th power. All right, so this right here would be the expanded version for that binomial raised to the 5th power. Again, if you want to go ahead and try and just FOIL it out over and over and over again and see if you get the same thing, that's fine. Or you can practice using Pascal's triangle. And I tried to be as clear with writing out the work as possible, but if you get pretty good with your exponent rules, you can do it much faster. Here's number 15. All right, so I'm going to go ahead and put this x plus 5 as our divisor off on the side. And then for our dividend, we have this longer polynomial. We have this 4x to the 3rd power plus 17x squared minus 10x plus 25. So I was saying earlier, number 13, I would go over some long division and synthetic division. So here we go. First thing we have to do is try to get this 1st degree term here to match this 3rd degree term here. And so if you multiply something by 1st degree to get 3rd degree, it's got to be 2nd degree. So I'm going to go ahead and put 4x to the 2nd power. I'm going to line up our degrees on top of each other. So notice how these are my 2nd degree terms. So if we go ahead and multiply this 4x squared by this x, that's going to be 4x to the 3rd power. We always want these terms to match so that when we subtract, we get 0. But keep in mind, we have to also multiply 4x squared by this 5. So that's going to be plus 20x squared. 20x squared. Go ahead and give that a hug, and then we're going to subtract to see what the remainder is, just like regular long division. And keep in mind that like kind of all the degrees match, right? These are cubic terms, these are quadratic terms, so just keep those organized. These should always subtract to get 0 when you are subtracting here. Now if you do this 17x squared minus this 20x squared, that's going to be this negative 3x squared as a remainder. Let's go ahead and bring down this minus 10x. All right. Now let's just repeat the process again. This is a linear term, it's raised to the first power. What are we going to put up here to multiply it by to get this negative 3x to the second power? Let's go ahead and put a minus 3x, right? Because linear times linear is quadratic. So this minus 3x, let's go ahead and multiply by both of these. So negative 3x times x is going to be negative 3x squared, so that matches perfectly. And negative 3x times 5 is going to be negative 15x. Let's go ahead and give that a hug and subtract, see what the remainder is going to be here. This negative 3x squared minus negative 3x squared is going to be 0, so that cancels out. And then this negative 10x minus negative 15x, that's going to be adding, so we're going to get positive 5x. Okay, so hopefully one last time here, we're just going to bring down this 25. I think this is going to work out really nicely. I don't think we're going to have a remainder, which is good. So what are we going to multiply this leading term here up here to get this 5x? We know it's going to be a constant because of the 25 here. That's a constant. So let's go ahead and just put a plus 5. And let's go ahead and take this 5 and distribute it to this x and this plus 5. Multiplying that out, we're going to get 5x plus 25. And going and seeing the remainder here, we're going to see that's going to end up being 0 just because everything here is going to cancel out here. So we know this is going to go in perfectly nice. Okay, so we have our quotient here up at the top. And so this right here would be our solution. All right, now synthetic division is a little bit different. For synthetic division, we're going to go ahead and take a look at our divisor here and just see what would make this 0, and that would be negative 5. So we're going to go ahead and use that as our value on the side here for our synthetic division. That's what we're going to see what's going into. And we just take all our coefficients. Be aware to make sure we have every degree on the way down. So it looks like we don't have to put any placeholders of 0, but it looks like we have a 4. Going to put a 17, a negative 10. Just take those coefficients, and then let's go ahead and put a 25 here. Okay. Now I'm going to go ahead and just draw a line here just to stay organized. Okay. The first thing we're going to do here is just bring the 4 straight down, and then we're just going to go ahead and multiply this negative 5 times 4. That's going to be negative 20. Okay. And then if we go ahead and add this 17 and negative 20, or just 17 minus 20, we're always going to subtract here. It's going to be negative 3. All right, so keep in mind, if you take a look here, this 4 actually will match the 4s here. This negative 3 is going to match these negative 3s here. So hopefully you can see some patterns here as to why these are similar ways of solving the same type of problem. So then you multiply negative 3 times negative 5, that's going to be positive 15. And then if you go ahead and add these two together, we're going to end up with 5x, or just 5 rather. But notice how we have these 5x's here, which is why I was saying that. And then if we multiply negative 5 times 5, it's going to be negative 25. And if you add these, you're going to see a remainder of 0. So the fact that we have a remainder of 0 here lets us know that this was divisible with no remainder. And hopefully you can see some similarities and differences between synthetic division and using our polynomial long division. All right. And what these numbers at the bottom here signify are the coefficients and constants for our quotient here. So we can go ahead and say that 5 is a constant, so negative 3 must be linear and 4 must be quadratic. So our quotient here will be 4x squared minus 3x and then plus 5, right? And that, again, that 0 lets us know that we have a remainder of 0 and it went in evenly. All right, for number 16, let's take a look at using the rational zeros theorem to determine the zeros for the following function. All right, so we have this polynomial function here. It's a quintic one, so it's raised to the 5th power. So we could have up to 5 zeros here. Now to get this started using the rational zeros theorem, we want to remember that we really care about the first leading coefficient as well as the constant at the end here. So keep in mind this negative 12 here, this is going to be p, and then this 2 over here is going to be q. So we can get a list of all the possible rational zeros if we take the ratio of our p factors and our q factors. Okay, so let's see, what are all our factors of p? Well, we have plus or minus 1. Those are both factors of negative 12, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So think about the positive factors as well as the negative factors of that number. And then for 2, it's a little bit easier. We just have plus or minus 1 and plus or minus 2. All right, now if we go ahead and take all of these factors here and divide them by 1 or -1, we're actually just going to get those original factors themselves. So this would be, all of these would be possible rational zeros that we can add onto our list here. And then we have to go ahead and take all of these on top here and also divide them by 2 and get rid of any duplicates. So 1 over 2, that would be a new one. That's going to be plus or minus 1/2. Okay. However, if we do 2 over 2, that's the same thing as 1, so we already have that one. 3 over 2 is going to be new, so I'm going to say plus or minus 3 over 2. Again, these are all possible rational zeros. 4 over 2 is just 2, so I'm not going to write that one. 6 over 2 is just 3, we already have that one. And 12 over 2 is just 6, and we already have that one. So if we're going to have any rational zeros, they would be along this list here, okay? If we have some zeros that are going to be imaginary or irrational, they're not on this list. All right, so sometimes it's a little bit of trial and error, but we're going to go ahead and just start with one of these values and give it a go. So I'm going to go ahead and start with +1. So if I'm going to choose +1, I'm going to use synthetic division here. I'm going to put a 2, a -4. I'm going to write those coefficients down, -7, 14, 6, and -12. And let's go ahead and see if we get no remainder here, which is what we're looking for. So this 2 comes straight down. 2 times 1 is 2. -4 plus 2 is -2. 1 times -2 is -2. Adding these, we get -9. 1 times -9 is -9. Adding here, we get +5. 1 times 5 is going to be 5. 6 plus 5 is 11. 1 times 11 is 11. -12 plus 11 is -1. So we were super close, but that's not going to be one of our rational zeros there. So that's not going to work, but let's try something else here. I'll go ahead and try 2. So I'm going to take 2. And just repeat the process here. I'm going to take this 2, -4, -7, 14, 6, and -12. Let's go ahead and try this again. And it's a little bit of just trial and error here, right? So this 2 comes down. 2 times 2 is 4. We got a 0. 2 times 0 is going to be 0. Plus -7 is -7. This is -14. This one's a little promising. We get 0 here. 2 times 0 is 0. 6 plus 0 is 6. Here we get +12 and a 0. So this is great because now we know that this 2 here is one of the zeros. Okay, so I'm going to go ahead and just make this smaller and put it on the side. So put that right over here. So what we just identified is that if 2 work, that means x minus 2 would be a factor or a linear factor or binomial that goes into this evenly. Now, what do the rest of these numbers down here mean? Well, it means that the other polynomial that we multiply by x minus 2 to get the original polynomial has a constant of 6, has no x term, has a -7x squared, has 0x cubed, and has 2x to the 4th power. So I'm going to go ahead and write that out here. So we have 2x to the 4th power plus 0x to the 3rd power. I'm not going to write it, minus 7x squared, and then it's going to be plus 0x. I'm not going to write it, and then plus 6. All right, so this would be what those numbers down there represent. This actually looks pretty interesting to me. I think we can actually factor this thing out. So I'm going to go ahead and actually move this up a little bit so I have some more space to work with. But we're going to leave this x minus 2 alone. And now for this polynomial over here, notice how this is x squared, but if you square that, you get this x to the 4th power. So what I'm thinking here is creating a higher degree kind of quadratic pattern here, but I think we're gonna have something x squared and something x squared here. I believe we're gonna have minus and minus, so I think this is gonna factor, but feel free to pause if you wanna go ahead and try to factor it as well. I think for the first one, I think I'll try x squared. I think we'll do minus 2 and minus 3 because -2 and -3 do multiply to get positive 6. So, and I think we need a 2 somewhere in there to get that 2x to the 4th power. So I'm going to go ahead and put the 2, I think over here. Let's go ahead and try this. So x squared times 2x squared is 2x to the 4th. This is going to be -3x squared. This is going to be -4x squared. If you combine those, you do get this -7x squared. And then minus 2 and minus 3 do get positive 6 when you multiply them together. So we're going to try to determine the zeros here. It's when each of these are equal to 0. So let's see if we can figure that out here. If we look at this first one, at this x minus 2, we already figured out that one of the zeros here is going to be x is equal to 2. That's one of our zeros. Let's see, another one of them is going to be this x squared minus 2. So how do we make that equal to 0? Well, if we take x squared minus 2 and set it equal to 0, add 2 to both sides, x squared would equal positive 2. So x equals plus or minus the square root of 2. Those would be 2 more zeros here. And then finally, if we take a look at this 2x squared minus 3, what if we set that equal to 0? Well, we have 2x squared minus 3 is equal to 0. Add 3 to both sides. We get 2x squared is equal to 3. Divide both sides by 2, so x squared will equal 3 over 2. And if we go ahead and take the square root of both sides, we're going to get that x is equal to plus or minus the square root of 3 over 2. Now this one we should go ahead and just rationalize, but if we go ahead and say that this would be, let's say root 3 over root 2, and if we multiply both top and bottom by root 2 over root 2, you would end up here with saying that this would be plus or minus, I think, root 6 over 2. So putting this all together, we could have up to 5 zeros, and it looks like we have all 5 of them. One of the zeros is going to be x is equal to 2. One of the other zeros here we just said a moment ago was going to be the positive square root of 2. So we can say positive root 2. We can also say it's going to be negative root 2. Go ahead and just kind of separate all these to show you all 5 of them. And then we're going to have this positive root 6 over 2. And then finally, we're going to have this negative root 6 over 2. So these would be our 5 zeros. We have one rational one, which is why it's on our list from over here. This is going to be 2 irrational zeros and 2 more irrational zeros, which is why they're not on our list of possible rational zeros. So using the rational zeros theorem, here are 5 zeros for this function. Moving on to part 5, let's take a look at some rational functions together. So in 17, let's consider the following function of f of x is equal to this negative x squared minus 3x on top over this x plus 3 on bottom. All right, so first thing we're going to want to do is factor if we can. So if we take a look at the numerator here, I think we can factor out a negative x. If we go ahead and do that, we're going to be left with a quantity of x plus 3. And we can see on the bottom here, we also have this x plus 3. So factoring these types of rational expressions can be helpful because you may see some things that you might not see otherwise. So in this particular case, notice how we have this x plus 3 binomial as well as this x plus 3 binomial on the bottom as well. Now, whenever we have these identical factors, we can go ahead and cancel them out. And so we're going to be left with this function of f of x is going to be equal to negative x, all right? Now, if you end up crossing something out, keep in mind that we're going to be having a hole there. So what would make a hole in this particular case? I'm going to go ahead and write it down. Because we crossed out these two factors, it kind of is hiding the fact that they were part of the function as it is, but there's going to be a hole at when x is equal to negative 3. All right, so that's just the value for x that a hole would be created, and we can go ahead and figure out some more information from there. Now, if you just wanted to visualize what this would look like, you can go ahead and graph it on a graphing calculator or on Desmos, but what we're going to find here is that when x's value is going to be negative 3, there's going to be a hole on here on our function. So x can't be equal to negative 3. You can also kind of see that on the bottom here, we're going to have a vertical asymptote because we can't divide by 0 here either, right? So for the domain, I'm just going to go ahead and say right now that x can be all real numbers, except x can't equal this negative 3. So I guess I could write it like this, where I could say it's going to be from negative infinity up until negative 3. And then I can say union and say it's going to go from negative 3 to positive infinity. So x can be anything except for negative 3. So if we go and plug in x equals negative 3 into this function here, we're going to get f of x, where f of negative 3 is going to be equal to the opposite of negative 3, or positive 3. So for our range values here, we can say that the function can be anything except for positive 3. So we're going to go from negative infinity up until positive 3. And then we're going to also say that the y values here can also be 3 to positive infinity, right? So it can't be equal to positive 3. Now, as for the vertical asymptote, that's when the denominator is equal to 0. So if we take a look here for the vertical asymptote, we can see that if x was negative 3, then we would have a vertical asymptote there. So we can say x is equal to negative 3. Now, as for the vertical asymptote, if this x plus 3 over here didn't cancel out with the one above, then we would have a vertical asymptote. But since it did, we're not going to have one. So we're going to say we're not having a vertical asymptote here. Now, as for a horizontal asymptote, we have a horizontal asymptote if these degrees of the leading term here are the same, or if the degree of the denominator is greater than that of the numerator. Whenever the numerator's degree is greater than the bottom or the denominators, then we're not going to have a horizontal asymptote. So we're also going to say there's no horizontal asymptote here. Now for the x-intercepts, we can just go ahead and make y equal to 0. So if we change f of x to 0, then we can go ahead and solve. The only way this would be true is if we get 0 in the numerator. And if we go ahead and see here, that would only happen if x was equal to 0. So So our x-intercept is going to be at 0, 0. And for our y-intercept, that's going to be when x is 0. So we can go ahead and plug in 0 in for x in each of these locations. And you're going to see that if we do that, we're going to get 0 over 3. And so that also is going to be the y-intercept of 0, 0. So we know this function is going to go through the origin. And hopefully that makes sense because this is just this negative x and our y-intercept is going to be 0. There's really a plus 0 here if you're writing this in slope-intercept form. Okay. If we do have a hole, we did say earlier that we have one when x is equal to -3. So we can go ahead and say that we have a hole at x equals -3. And for a hole, we said earlier that's going to occur when x is equal to -3 because those x plus 3 terms, or factors rather, canceled out. If you want to go ahead and find out where the exact hole is, you can plug a -3 into the function we have here. You're going to see it's located at -3, +3, that there's going to be a hole right on our line there. Let's check out number 18. In number 18, we have the function here, f of x is equal to this 2x minus 9 in the numerator over this 3x plus 5 in the denominator. These are both linear binomials, so it doesn't look like they have any common factors we can kind of factor out using a GCF or anything, so I think we're going to be stuck here. And so from here, let's go ahead and see what we can figure out. So let's go ahead and start with the vertical asymptote. Remember, that's going to occur when the denominator is set equal to 0, and we don't have to worry about holes in this case because nothing's going to be canceling out at all. But if we set the denominator equal to 0, then we should be able to find out where the vertical asymptotes are. We can take away 5 from both sides and say 3x is equal to -5, and divide both sides by 3 to say x would be equal to -5/3. So we'd have a vertical asymptote at x equals -5/3. Okay. While we're on the topic of holes, I'm just going to say there aren't going to be any in this case because we can't cancel anything out. For the horizontal asymptotes, that's going to be up to looking at the degrees of these leading terms, or the highest degrees here, rather. So notice how we have these matching degrees of x to the first power and x to the first power. Whenever that's the case, our horizontal asymptote is just going to be the ratio of these leading coefficients. So this 2 and this 3 is going to be where our horizontal asymptote is going to be. So a horizontal line is going to be y equals, and because we have matching degrees on top and bottom, it's just the ratio of their coefficients. So we have this horizontal asymptote at y equals 2/3. All right, so just so we can visualize this a little bit, we do have this vertical asymptote at x equals -5/3, and we have this horizontal asymptote at y is equal to 2/3. What I'm going to do next is find the x-intercepts, and remember, to find the x-intercept, that's when y is going to equal 0. So go ahead and make y equal 0 here. I'm going to actually write this one out. It's going to be 0 is equal to this 2x minus 9 over this 3x plus 5. If we go ahead and multiply both sides by 3x plus 5, we're going to get 0 is equal to this 2x minus 9. If we go ahead and add 9 to both sides, we're going to get 9 is equal to 2x. And divide both sides by 2, we're going to say x is going to be equal to 4.5. So that's going to be our x-intercept here, is going to be at 4.5, 0. So we do know we're going to have that point as a point on our graph. It's going to be maybe somewhere over here. I'm going to put right on our x-axis. Now what about the y-intercept? Well, to find the y-intercept, that's going to be when x is equal to 0. So I'm going to go ahead and plug that in. Let's see, we're going to say that y would be equal to 2 times 0, which is going to be 0 minus 9, over 3 times 0, which is going to be 0 plus 5. So this is going to simplify to -9 over 5, which then simplifies down to equaling -1.8. So our y-intercept for this function is going to be 0, -1.8. And so 0, -1.8 would be just about here. Now, just making a rough sketch here, this rational function would look something like this, where it's curving up and approaching those asymptotes. And if we know that's going to be over there, then the other part of this function, as you might have seen in rational functions in the past, is going to look something like this. But feel free to put it on a graphing calculator or plug in points to get some more accurate points. Now for the domain, it looks like x can be any value except for whatever the vertical asymptote is going to be. So for the domain, I'm going to say it's going to be from -infinity all the way to -5/3. It's going to take a pause there at the vertical asymptote, and it's going to, all the x values are going to continue afterwards. So from -5/3 up to +infinity. All right, so that's going to be the domain. As for the range, it looks like we can have any y value except for the horizontal asymptote value of y is equal to 2/3. So for the range, it looks like it's going to be everything's good from -infinity up until 2/3. It's going to take a pause at that horizontal asymptote. Then it's going to go ahead and continue after 2/3 up to +infinity. All right, let's check out number 19. In number 19, we have another rational function. We have f of x is equal to this x squared plus 3x plus 2 on top, and then we have this x minus 2 on bottom. Now, the bottom doesn't look like it could be factored just because it's linear, and I don't see any GCS between these two terms. The numerator, however, looks like it can be factored. I'm going to go ahead and factor into the quantity of x plus 2 times the quantity of x plus 1, right? So got excited for just a moment. I thought there might be a hole, but it looks like there's not going to be just because we have an x plus 2 and an x minus 2, so I don't think we can cancel anything out here. So in terms of holes, let's go ahead and just write at the bottom here that we're not going to have any holes for this particular function. That being said, we can go straight to looking at the vertical asymptote because that's pretty quick to identify. So what makes that denominator equal to 0? Well, if x was equal to positive 2, we would have a 0 in the denominator. So we know we're going to have a vertical asymptote there. Now, what about a horizontal asymptote? Well, I said earlier that we're not going to have a horizontal asymptote when we have a degree higher than the bottom, and we're looking at the degree of the numerator and the degree of the denominator. However, we could have a slant asymptote if we have a degree 1 higher in the top than the bottom. Now, when we look at back at number 17, it's also 1 higher than the bottom. However, we saw that we had a hole because one of the factors canceled out. So in this case, nothing's canceling out, so we know we're not going to have a horizontal asymptote. But instead, we're actually going to have maybe a slant asymptote. So I'm going to go ahead and cross this out and write slant instead. So be on the lookout if you see the degree of the numerator is 1 degree higher, exactly 1 degree higher than the denominator. All right. So if you want to find out what that slant asymptote is going to be, what you actually do is perform long division, polynomial long division, to figure out that equation of that slant asymptote. So we'll go ahead and take this x minus 2, and let's divide that into this x squared plus 3x plus 2. And of course, you could use synthetic division as well. I'm going to go ahead and put an x on top here. So x times x is x squared. X times negative 2 is negative 2x. We can go ahead and subtract here and see what the remainder is. The x squareds are going to cancel out. The 3x minus negative 2x is going to be 5x. We're going to bring down this positive 2. And then I think we're going to go ahead and put a plus 5 up here. So 5 times x is going to be 5x. 5 times negative 2 is negative 10. Give this a hug and subtract. The 5x's cancel out here, and then 2 minus negative 10 is going to be a positive 12. So the remainder here is insignificant. However, we know the slant asymptote equation is going to be y is equal to x plus 5, which is really just what we had in the quotient there, this x plus 5. So this is insignificant over here. So you just need to know what's on top for the equation of that slant asymptote. All right, for our x-intercepts, that's going to be when y is equal to 0, and that's only going to happen when the numerator is equal to 0. So you could set this up and then multiply both sides by x minus 2, but that's just going to go ahead and cancel out. So I'm just going to go ahead and say that 0 is equal to x squared plus 3x plus 2. Hopefully that makes sense because 0 divided by anything would be 0, so we just really care about the numerator equaling 0. And we already knew we can factor this. We can turn this into this quantity of x plus 2 times the quantity of x plus 1. And so what values of x would make this true? That would happen when x is equal to negative 2 and when x is equal to negative 1. So there's going to be two x-intercepts here. One's going to be at negative 2, 0. The other x-intercept is going to be at negative 1, 0. So we're going to have two x-intercepts here. Now what about for the y-intercept? The y-intercept is going to occur when x is equal to 0. So we can go ahead and say that y would be equal to 0 squared, which is 0, plus 3 times 0, which is 0, plus 2. All over this 0 minus 2. Now on top we're going to have just a 2, on bottom we have a negative 2, so we're going to have a y-intercept at when y is equal to negative 1. So we're going to say at 0, negative 1, we're going to have a y-intercept. Let's go ahead and get this out of the way a little bit so we can see a graph. So just so you can visualize this a bit, at x equals 2 we have a vertical asymptote, and at the equation y equals x plus 5 we have a slant asymptote. We're going to have two x-intercepts at x equals negative 1 and x equals negative 2. We're also going to have a y-intercept at 0, negative 1, so something down here. Now if we go ahead and make a rough sketch here, our rational function is going to look something like this on this lower part of our graph. And then for our upper part of the graph, it's going to look something like this. Just a rough sketch. Now feel free again to use a graphing calculator or plug in points to get more accurate sketches. Now for the domain, looks like everything is good for the x values, except when we get to the vertical asymptote of x equals 2. So we can say from negative infinity up until positive 2, as well as anything after positive 2 up to positive infinity is fair game for the domain. As for the range, it looks like everything's going to be fine in terms of the y values because we don't have any slant asymptote. Now, as for the range for this function, I'm actually going to go ahead and just talk about it conceptually and not actually find out the values because we don't really need to know that right now for this. However, keep in mind that the y values seem to go down forever. So it would go from negative infinity up until this y value here. There's going to be a little cap. You could just use a graphing calculator to help you find that turning point to figure out this highest point over here. Then notice how the function's not going to exist until we have a minimum over here for this upper part of the function. And then, of course, this graph is going to be going up forever as well. So for the range, it's going to be taking a break between these two lines over here. So it's going to have two parts from negative infinity up until this part here. And then it's going to start again from this y value and then go up forever from there. So I'm actually going to go ahead and not put the range for this particular case. Not that it doesn't have one, but you can just use a graphing calculator to figure that out, or we could talk about that in another time. So if you'd like to see that, just comment below. Okay, let's talk about number 20, where we have another rational function. We have f of x is equal to x squared plus 2x minus 3 all over this x squared minus 5x minus 6. Now we do have two quadratic expressions in the numerator and in the denominator. I think we can go ahead and factor this a bit. So in the numerator, I think it's going to be the quantity of x minus 1 and times the quantity of x plus 3. And for the bottom here, it looks like we can turn that into x minus 6 and x plus 1. All right, so right off the bat, it doesn't look like we're going to have any holes just because nothing is going to cancel out, so no holes for this particular function. But we can go ahead and start taking a look at some other pieces or attributes here. So looking at the vertical asymptotes first, we can see what x could be that would make the denominator equal to 0. Looks like we would have two vertical asymptotes here, one at when x is equal to positive 6 and when x is equal to negative 1. So we're going to have two vertical asymptotes here. For the horizontal asymptotes, we're going to look at the highest degree terms for the numerator and denominator. They're both x squared, so they're tied for having the highest degree. So we're just going to look at the ratio of their leading coefficients. They both have a 1 in front, so 1 over 1 means that we're going to have a horizontal asymptote at y is equal to 1. All right, now moving on to our x-intercepts, that's going to be when y is equal to 0. Keep in mind that when we're finding the x-intercepts, we really can just set the numerator equal to 0 just because the denominator is going to cancel out when you multiply it by 0 anyway. So we're going to 0 is equal to, and I'm just going to write the factored version of the numerator just because it's going to be easier to use. So it's going to look just like this. And so we're going to have two x-intercepts. One of them is going to be at 1, 0. So 1, 0, since if x is 1, then the whole right side of the equation becomes 0. And if x is equal to negative 3, then we would also get 0. So we have two x-intercepts here of 1, 0 and negative 3, 0. Now, as for the y-intercept, that's when x is going to be equal to 0. So we're going to say f of x is the same thing as y. We're going to have 0 squared, which is 0, plus 2 times 0, which is 0, minus 3, all over the 0 squared, which is 0, minus 5 times 0, which is 0, minus 6. So altogether here, we're going to get negative 3 over negative 6, which is just going to simplify to positive 1/2 here. So we're going to have a y-intercept for this function at 0, 1/2. All right, so looking at this on a graph, we're going to have a vertical asymptote at x equals 6, a vertical asymptote at x equals negative 1, a horizontal asymptote at y equals positive 1. We'll have two x-intercepts at x equals positive 1 and at x equals negative 3, something like here and here. We're also going to have a y-intercept at 0, 1/2, so it's maybe something like right here. And so I'm going to go ahead and make a rough sketch of what this would look like. Feel free to plug in some points to get a more accurate sketch. I'm just making a real rough sketch. In this middle section here, it's going to be approaching that vertical asymptote. Keep in mind they are allowed to cross horizontal asymptotes, just not cross vertical asymptotes. And finally, on the right side of the function, we're going to have something along the lines of this. This would look like the curved part on the right side here, approaching those two asymptotes as well. Now, the domain has three parts here. It's going to go from negative infinity all the way up until negative 1. It's going to take a pause. It's going to go from negative 1 all the way to positive 6. Then it's going to take a pause. Then from 6 all the way up to positive infinity. As for the range, it doesn't look like this function needs to take a break at all. There's no holes or anything either, so I don't have to worry about that. But you can see that middle section of this graph shows that the range is going to go from negative infinity to positive infinity. All right, now that we reviewed some rational functions, let's move on to some radical functions. In part 6, let's take a look at some rational functions together. So in number 21, let's go ahead and solve for all the possible values of x. So we have the square root of 12 minus x is equal to x minus 6. So first thing we're going to do here is see where the radical is. We can see the radical is on the left side of this equation. Now, if this is a square root, then what's the inverse operation? Well, the inverse is going to be raising it to the second power. So let's go ahead and raise both sides of this equation to the second power. All right. Now on the left side, that 12 minus x is grouped together in parentheses. We just don't write it, it's just implied. So we're going to have this 12 minus x on the left side of the equation. And on the right side, I could just FOIL that out, but I'm just going to go ahead and expand it to make it a little bit more clear. But feel free to just go ahead and FOIL it out if you can. But we're going to have this 12 minus x on the left side. On the right side, x times x is going to be x squared. X times negative 6 is negative 6x, but there's going to be two of them for the outers and the inners, so it's going to be minus 12x. And then this negative 6 times negative 6 is positive 36. So feel free to pause or spend some more time on that, but that would be that as the FOILed out trinomial. Now I'm going to go ahead and take away 12 from both sides here, and I'm also going to add x to both sides here. So I'm going to move everything basically to the right side of the equation. So I'm going to leave that x squared alone. There's no like terms with it. If we go ahead and add x to both sides, this is going to become a minus 11x. And if we take away 12 from both sides, that's going to be plus 24, since 36 minus 12 is 24. Now you can go ahead and solve this quadratic equation using a few different methods. I'm always going to try to factor first. I think this one is factorable, but you could use the quadratic formula or completing the square, although I wouldn't do that since b is odd here. But I think I'm going to go with a minus 8 minus 3 here. Let's go with x minus 8 and x minus 3, right? We need two negatives to get positive 24 and two negatives to add to get to negative 11. Those would be those two factors of x minus 8, x minus 3. Now using the zero product property, what would make each of these binomials equal to 0? Well, for this one, if x is 8, for this one, if x is 3. So our two solutions here, at first glance, is going to be x equals 8 and x equals 3. But of course, with these types of equations, these radical functions or radical equations, we should check for extraneous solutions, right? So if we take this 8 over here, and if we plug it in to where x is, let's see if we are going to get something that is true or not. So first up, let's go ahead and take the square root of this 12 minus 8 and see if that's equal to, I'm going to put a little question mark here to see if it's equal to 8 minus 6. Okay, now 12 minus 8 is going to be 4, so we have the square root of 4. Is that equal to 2? Again, we only take the principal root or the positive root here, so we're going to say 2 does equal 2, so this one does work out. So this would be one of our solutions. Let's see about the other one though. If x is equal to 3, let's take this 3 and substitute it in and see if this is true. We take the 3, it's going to be the square root of 12 minus 3. And let's see if that is equal to 3 minus 6. I'm going to put a question mark because we're not sure yet. 12 minus 3 is going to be 9. The square root of 9 is going to be 3. Let's see if that's equal to this negative 3, and that's not. So we're going to go ahead and just say at this point we know this is not going to be true. I'm going to put a slash through that equal sign. So this x equals 3 is an extraneous solution, so we're not going to use it. Even though we got it algebraically, it doesn't work when we plug it back in. All right, so x equals 8 would be our solution for number 21. All right, let's check out number 22. All right, in number 22, we have to solve for all the possible values of x again. We have x is equal to the square root of x minus 1 plus 2. Now, just like in the last one, we want to get this by itself. In the last problem, though, this radical is already by itself. Let's go ahead and take away this 2 from both sides so we can isolate the radical. If we do that, we're going to get x minus 2 is going to be equal to the square root of this x minus 1. All right, so always get this radical isolated the best you can. Now, what's the inverse of square rooting? Well, it's going to be squaring or raising to the second power. So let's go ahead and do that to both sides. On the left side, I'm not going to write out the binomials. I'm just going to square this and multiply it out and FOIL it. So feel free to pause if you need to do so. If we go ahead and FOIL it out, it's going to be x squared. It's going to be minus 4x, and then it's going to be plus 4. Okay. On the right side, the square root and square cancel out, so we just have x minus 1. Now let's go ahead and take away x from both sides so that we can move everything to the left side and add 1 to both sides so we can set this quadratic equation equal to 0. If we go ahead and do that, we're going to get x squared, and then it's going to say minus 5x, and then it's going to say plus 5 is equal to 0. All right, so at this point, we have a quadratic equation. It's set equal to 0. We could try to factor. I don't think we can do so here. Completing the square is more friendly when this is an even number, so I don't really want to do that. So I'm going to go ahead and use the quadratic formula here. Okay, so I'm going to go ahead and say x is equal to, it's going to be the opposite of b, so negative 5 is 5, plus or minus the square root of, and inside here we're going to have the discriminant, so it's going to be b squared, which is negative 5 squared. Negative 5 squared is 25. Minus 4ac, so it's 4 times 1 times 5, all over 2a. So 2 times 1 is just going to be 2. Cleaning this up just a little bit, I think we're going to have 5 plus or minus 4 times 1 times 5 is 20. 25 minus 20, we're going to have the square root of 5 all over 2. And so it looks like we're going to have two solutions here from this algebraically. So we're going to say x is going to be equal to 5 plus the square root of 5 over 2. And we can also say that x would be equal to 5 minus the square root of 5 over 2. So we have these two solutions algebraically, but we should check to see if we have any extraneous solutions. Let's go ahead and plug this solution in for x over here and in over here. You can go ahead and just do that on a calculator if you would like, just to see what the values are going to be. I'm just going to write out what you would type in though. You would have this 5 plus root 5 over 2. Algebraically, this is probably going to be a little bit messy, so feel free to just plug it in to see if you get the same decimal value. We're going to see, would that be equal to the square root of, and plugging this in, it's going to be 5 plus root 5, that's x, right? And then minus 1, that's all underneath this radical, and then plus 2. Okay, so if you go ahead and plug that into a calculator on the left side and on the right side and see what you get, you should get about 3.61 on the left side, and that should be equal to, and you plug it in on the right side, you're going to get 3.61 again. So this does equal each other, so we know this would be one of our solutions, right? So it's not extraneous, but we could also plug in the other one here and see if that's going to make sense. So it's going to be the same thing, just with a minus, right? So I'm actually just going to copy this over here. Okay, actually I'm going to put it down here below and then give a little space here. So I'm just going to do that and then make these both minuses, right? Because it's basically the same thing. And let's see if this is equal to each other. Plugging this into a calculator, we're going to get about 1.38 on the left side. And on the right side here, I'm getting about 3.56. So these are not equal to each other. So this would be an extraneous solution. And on the other side, we're going to get about 2.62. So you can see here that these are not the same. So the other solution here, or this 5 minus root 5 over 2, is an extraneous solution. All right, let's check out number 23. All right, in 23, we have a radical on both sides of the equation. So for these types, it's going to be a little bit trickier to solve because we can't really isolate it. So we do have one of them already isolated, which is good. The one that has two of these terms inside the radical, I like this one isolated just because if we go ahead and square both sides, then that one doesn't have a radical. It's going to be easier to deal with this under a radical instead. So what I'm going to do first is this right side is going to be cleaned up a lot better. The left side is going to be a little messy, but this is the better alternative than if you had the 8x square rooted on itself. So when we square both sides here, this is going to clean up the right side really nicely. However, the left side is going to be messy for a little bit, but we'll just deal with that as we go. So on the left side, I'm actually going to write this out so it's a little bit more clear, just because this is going to be a little bit trickier to deal with. So we have the square root of 8x minus 2 multiplied by the square root of 8x minus 2. And on the right side, we're going to have the, if we take the square root of 3x minus 2 squared, that's just going to be 3x minus 2. Okay. Now on the left side, if we go ahead and FOIL this out, the square root of 8x times the square root of 8x is just going to be 8x. Then we have this minus 2 times the square root of 8x, but we have two of them, so it's going to be minus 4 times the square root of 8x. Then we have this negative 2 times negative 2, which is positive 4. This is going to be equal to this 3x minus 2 on the right side of the equation. Next, I'm going to go ahead and take away 8x from both sides and take away 4 from both sides. I really would just want to try to isolate this 8x the best I can here. So if we do that, I'm going to be left with this negative 4 times the square root of 8x is going to be equal to, and if we take away 8x from both sides, it's going to be negative 5x. And if we take away 4 from both sides, it's going to be minus 6. Next, if we go ahead and divide both sides by negative 4, we're going to have the square root of 8x is going to be equal to, And I guess I'm just going to write this as a fraction here for now, but I'm going to have this 5x minus 6, rather this negative 5x minus 6 over this negative 4 for a moment. All right, now to get rid of this radical, let's go ahead and square both sides of this equation. That way we have no radicals left in the equation. On the left side, squaring this square root of 8x, we're just going to have 8x on the left side. On the right side, though, we're going to have to multiply this out. So it might be a little more clear just to be a little bit more specific. So it's going to be negative 5x. Actually, if everything's negative here, let's go ahead and rewrite this. So a negative over negative is a positive, and a negative over negative is a positive. So we could also just rewrite this as 5x plus 6 over 4, right? Same thing. And then this is going to be the same thing as 5x plus 6 over 4. All right, since we have negatives over negatives, so we can just pull out a negative 1 essentially from top and bottom. So let's go ahead and see. We have no more radicals, which is good. It is a little messy here with these fractions. We also have these binomials on top, but that's okay. When we multiply fractions, we just multiply the tops. I know it's a little bit more involved here, but we still are following the same multiplication rules and multiply the bottoms here. So the bottom's going to be easy. It's just going to be 16. The numerator is going to be a little bit longer, but it's a perfect square trinomial. So we're going to get 25x squared. Just make sure you FOIL here. And it's going to be plus 30x. So it's going to be plus 60x. And then the 6 times 6 is going to be 36. So it's going to be plus 36. All right. Let's go ahead and now multiply both sides by 16. If we do that, then we're going to end up with, let's see, 80 plus 48 is going to be 128. So I'm thinking 128x is going to be equal to 25x squared plus 60x plus 36. All right, so now we have a quadratic equation. We can set this equal to 0, so it's in standard form. So we have 0 is equal to, keep that 25x squared, taking away 128x from both sides. 60, take away that 128 is going to be negative 68, so minus 68x, and then it's going to be plus 36. So we have this quadratic equation, and it looks a little intimidating with these coefficients. I don't really want to use the quadratic formula if we don't have to, so I'm going to try factoring. You could try 5 and 5. I'm going to try 25 and 1, 25x and 1x, and just see, just because these numbers are pretty big, I think we'll need to multiply it out. So let's see, if we do 25, let's do maybe 2 and 18. So if I do minus 2 here and I do minus 18 here, let's see if that works. This would be 25x squared. Okay, that's good. This is going to be minus 50 and minus 18x. So that is minus 68x. Okay, cool. And then we have this minus 18 times minus 2, which is positive 36. So these would be the two binomials. Now, using the zero product property, what makes each of these become 0? Well, for this one, it's if x is equal to 18 over 25. So x would be equal to 18 over 25 for that one. And for this binomial, if x was equal to positive 2, then that would be another solution. Now, in the last couple examples, I've already gone over how to check for extraneous solutions. What you should do is plug this one in, this x equals 18 over 25 into the original equation. Plug that in right over here, and see if you get the same thing. I'm going to let you know right now that it's going to work. And also, if you plug in this x equals positive 2, these are both going to work. So I'm going to put these check marks here to show you that I did check these, and you should go ahead and try and do them as well if you just want to check, or just throw them in a calculator to make sure that the left side and right side are indeed equal to each other based on their principal roots. Okay, so let's go and check out 24 and see what we have going on there with another radical function. Number 24, let's go ahead and make a rough sketch of this function, then state the domain and range. So we have this function of f of x is equal to 2 times the cube root of this x minus 1 quantity plus 3. All right, so real quick, just to review, the cube root function looks like this. The parent function is going to be just f of x is going to be the cube root of x. The domain and range of this is going to be all real numbers. If you're dealing with a square root function, you have to be careful a little bit because you aren't taking square roots of negative values because you got imaginary numbers. But for cube roots, you can take the cube roots of positives or negatives. That's okay. If you want to look at what a general table is going to look like of values here, you want to think about what your perfect cubes are a little bit. So for the parent function, I'm going to go ahead and make a table just so you can visualize what this looks like if you've forgotten what this graph generally looks like. So if you plug in x is 0, then f of x or y would also be 0 because the cube root is 0, 0. Then using a perfect cube, the cube root of 1 would just be 1, and the next one would be cube root of 8 would be 2. All right. Same thing, if you go in the negative direction, the cube root of -1 is just -1, and the cube root of -8 is going to be -2. I think that's going to be perfectly fine. So for the parent function here, we're going to have 0, 0, which is going to be at the origin. Then we're going to have 1, 1, and then that's going to be over here. And then 8, 2 is over here, over in quadrant 1. Then we have -1, -1, and then we have -8, -2. So something like this. So making a rough sketch of the parent function, it's going to look something like this. So just imagine this when you're talking about these cube root functions. Now, what are the transformations that are being made here? This -1 lets us know that we're moving everything to the right 1. So that's going to affect the x value. So we have to add 1 to each of these x values here. This +3 means all the y values are going to be moved up 3 after they're multiplied by 2. So for each of the y values, we have to multiply them each by 2. We have a vertical stretch, and then we're going to have to add 3 onto that afterwards. So if we go ahead and do that for our function here that we have in this particular problem, let's see, I'll make a new table here at the bottom so you can see what this looks like. Let's go ahead and make 5 values here. 1, 2, that's 3, that's 4, that's 5. And then so if we go ahead and add 1 to each of these x values, we're going to get -7, 0, and then we're going to have 1, 2, and 9. -2 times 2 is -4, plus 3 is going to be -1. -1 times 2 is -2, plus 3 is going to be 1. 0 times 2 is 0 plus 3, which is 3. 1 times 2 is 2 plus 3 is going to be 5. And then 2 times 2 is 4 plus 3, which is going to be 7. So if we go ahead and plot each of these points, kind of our central point to kind of think of is going to be 1, 3. That's kind of going to be our point of inflection here. And then if we plot each of these other points, we have 2, 5. So that's going to be up here. And then we're also going to have 0, 1, which is down here. And then we're going to have 9, 7, which is going to be all the way up here. And then we're also going to have -7, -1, which is going to be down here. So this right here would be a rough sketch using about 5 points for the parent function, and you can see the transformations that occurred based on what we saw in the function. So the -1 here is really telling us we're moving to the right one, so I'll put R1 for the right one. This +3 over here is telling us we're going up 3. I'm going to put a U3 for up 3, and then this 2 here is going to be a vertical stretch. I'm going to say just times 2, that's a vertical stretch, so it's pulling it upwards a little bit. Now, as for the domain of this function, the domain is going to be all the possible x values here. So it looks like it's going to be going to the left forever, so -infinity, and it's going to the right forever, so it's going towards +infinity. And if we want to throw the range on here, there doesn't look like there's anything limiting the y values for this function either. So for the range, it looks like it's going to be approaching -infinity as we go down to the left. And as we go up to the right, it looks like it's going to keep going up as well. So it's going to go towards +infinity. And it's safe to say for our cubic functions, or cube root functions rather, that we're going to have the same domain and range. There's no restrictions on them. Alright, so that wraps up some practice problems dealing with some radical functions. Keep in mind that numbers 21, 22, 23 were all dealing with square root functions, and 24 is dealing with a cube root function. If you want to go ahead and look at what square root functions look like, just go ahead and maybe graph them on Desmos or check out another video on that topic. In section 7 or part 7, let's take a look at some exponential functions together. In 25, it says to describe the transformations of the graph f of x is equal to 4 times 2 to the x minus 1 power minus 3. Let's go ahead and state whether the function is a growth or decay function, as well as a domain and range. Okay, so let's think about this for a moment. If we just want to know what the parent function is, the parent function here is going to be f of x is going to be equal to 2 to the x power. So we're going to ignore this 4 over here, as well as the -1 and the -3. So this right here, this f of x is equal to the x power, is going to be the parent function. Now, in determining whether this is a growth or decay function, we look at the base of the power. If the base is greater than 1, then we know we have a growth function, just because anything bigger than 1 raised to a positive power is just going to keep getting bigger and bigger and bigger. However, if this was a proper fraction, like 1/2 or 1/3 or something less than 1, you could use a decimal too, then you'd have a decay function, because any proper fraction raised to a positive exponent is going to get smaller. So this is going to be a growth function here. And just to visualize this parent function before we even look at transformations, it's going to look something along the lines of this, which is an exponential growth function, and it has a y-intercept of +1. Now, if we wanted to just create a table for this parent function, if x was equal to 0, then 2 to the 0 would be 1. If x was equal to 1, then y or f of x would be 2. If x was 2, then we would have 4. If x was negative 1, that'd be 2 to the negative first power, or that'd be 1/2. And if it was 2 to the negative second power, then that would be 1/4. So if you want to go ahead and plot those points, maybe it would look something like that on that graph above I sketched. Now, what kind of transformations are being made on this function? Well, we want to know that this -1 means that we're moving things to the right 1 unit. And we also want to know what this -3 means is it's down 3, and this is a vertical stretch by a factor of 4. So we can go ahead and write a few things here. So we're going to be moving 1 to the right. So we're going to go ahead and write +1 for all the x values. As for the y values, the f of x values, we're going to be multiplying everything by 4, and then we're going to be subtracting 3. And so if we go ahead and add 1 to each of these x values, what would we get? We would get -1, 0, 1, 2, and 3. Those would be our x values for these points that are being transformed. And for our y values, let's go ahead and take each of these y values, multiply them by 4, then take away 3. So this 1/4 times 4 is 1, minus the 3 is going to be -2. Then we can take this 1/2, multiply it by 4, that's going to be 2, minus 3, that's going to be -1. Then we can take this 1 times 4 is 4, minus 3 is going to be 1. Then we're going to take this 2, multiply it by 4, that's 8, minus 3, that's going to be 5. And then this 4 times 4 is 16, minus 3, that's going to be 13. And if we went ahead and sketched this, it would look a little different than what we had before, but the same general pattern. It would look something along the lines of this, where it's moved down 3, but to the right 1. And it's going to grow a little faster just because we have that 4 in front instead of a 1. So in terms of the transformations, we have 2 of these translations. So we're going to go to the right 1 unit. And we also are going to say that we have another translation that is going to be down 3 units. So there's 2 types of translations, which is just left, right, up, and down. And then we have a vertical stretch here by a factor of 4. So everything that in the y direction is being multiplied by 4 as we're stretching everything vertically. All right, as for the domain and range, the domain you can see as we move to the left for this function, it's going to be, nothing's going to be stopping it from moving to the left. So it's going to go to -infinity, and you can see it's going to keep moving to the right here as well it's moving up. So for the domain here, we're just going to say for these exponential functions, especially this one here, the domain is going to be from -infinity to +infinity. And as for the range is going to be, again, the y values for how low and how high this thing can go. So while the parent function has a horizontal asymptote at y equals 0, or the x-axis, it's going to approach it. Our new function here that we're dealing with in this particular problem had a translation down 3 units. So our horizontal asymptote at y equals 0, that horizontal line got translated down 3 units. So our horizontal asymptote is going to be at y equals -3. So that means the function is going to get very close to it, but it's not going to touch it. So it's going to approach -3 on the low end, but nothing's going to stop it from moving up forever towards +infinity. All right, let's check out number 26. You deposit $4,000 into an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded quarterly. Now our compound interest formula is going to be A, or the account balance, which is equal to P, or the principal amount, what we put into the account first, multiplied by the quantity of 1, or 100%, which is the original amount, plus R, which is the interest rate, divided by N, which is the number of times it's compounded in a year. That whole quantity raised to the nt power, n being the number of times it's compounded in a year, and t is going to be time in years. Okay, so what do we know? Well, we know the principal amount here. We know P is going to be 4,000. That's the amount we're putting into the account. The interest rate we know is 2.92%, but we're going to have to turn that into a decimal. So slide it twice to the left, that decimal point, or divide it by 100. That's how you convert percents to decimals. So we're going to have 0.0292. That's going to be R. Always turn it into a decimal. For t, we're talking about 1 year, so we're going to say t is equal to 1. And then quarterly, that's how many times it's compounded in a year, so n is going to be 4 because we're compounding 4 times per year with that word quarterly. So let's go ahead and just plug all these values in. So the account balance is going to be equal to 4,000, what we start off with the principal, multiplied by 1 plus that interest rate of 0.0292. That's going to be over 4. And that's going to be raised to the nt power, or 4 times 1 power. Okay, so cleaning this up a little bit, we're going to have this 4,000 multiplied by, and cleaning up the inside of the parentheses is going to be 1.0073. If If it's not a nice decimal or anything, feel free to just keep that loaded in your calculator, that's fine. Then 4 times 1 is going to be to the 4th power, right? So this is kind of going to be our exponential function. Notice how, because this value is greater than 1, we know it's a growth function, and that makes sense because our money is going to grow with the interest rate. This is our principal amount, so that's going to be the y-intercept, what we start with. And then this is going to be our power of how many times we're compounding this in 1 year. So make sure we just take this and we raise it to the 4th power, then multiply by 4,000, unless your calculator does follow the order of operations, which is fine. But if we go ahead and plug this in, you're going to get approximately $4,118.09. So after 1 year, we would expect that $4,000 to turn into about $4,118.09. Here's 27. In 27, we're going to go ahead and create a table of points that lie on the function f of x is equal to 2 times 0.5 or half raised to the x power, and make a rough sketch of it. State whether the function is a growth or decay function. So now what we mentioned in 25 earlier was that if we had a base of the power that was greater than 1, like in number 25, we had this 2 here, we knew it was a growth function. Now if you go ahead and take this half though, this is the base of the power, this is less than 1, we're going to have a decay function here. So we're going to go ahead and write that it is a decay function. And hopefully that makes sense, because if you keep raising 1/2 or the base of the power to higher and higher powers, it's going to get smaller and smaller as you go. Now for the table here, I'm just going to choose x equals -2, then -1, then 0, then 1, then 2. Feel free to choose other values if you would like. This 0.5 here, I'm also going to think about it as just a fraction. So I'm going to rewrite this myself. I'm going to say this is going to be f of x is going to be equal to 2 multiplied by 1/2 raised to the x power. I prefer fractions here. So let's see, if x is equal to -2, if we plug that in, then let's see, it would be f of -2. That would be 2 multiplied by 1/2 raised to the -2 power. Now 1/2 raised to the 2 power would be 1/4. So the -2 power means it's going to be the reciprocal. So that's going to be 4, and 4 times 2 is going to be 8. So when x is -2, f of x or y is going to be 8. Then let's find f of -1. So let's go ahead and plug a -1 into this. So it's going to be 2 times 1/2 raised to the -1 power. 1/2 to the -1st power is really just reciprocal, is 2. So 2 times 2 is going to be 4. So that's going to be this value here. F of 0 should be a little bit easier. It's going to be 2 times 1/2 raised to the 0th power. 1/2 to the 0th power is just 1. 1 times 2 is 2. Hopefully you can see a pattern here that as you keep going down here, we're taking half of each of the previous one, or raising it to the -1st power. As you can see, as we go down the table here, as these exponents are increasing by 1 each time, you can see that our y values are actually getting smaller, hence the decay we said earlier. So f of 1 is going to be 2 times this 1/2 raised to the 1st power. 1/2 to the 1st power is a half. Half of 2 is going to be 1. Put a 1 here. And finally, f of 2 is going to be 2 multiplied by 1/2 to the 2nd power. Now, half times a half is a quarter, and 2 times a quarter is going to be a half. So that's going to be our last y value in the table here. All right, for a real quick sketch, -2, 8 would be somewhere here. -1, 4 would be something like here. 0, 2 down here on the y-axis, 1, 1 over here in quadrant 1, and then 2, half would be somewhere like here. So a rough sketch would look something like this. This would approach the x-axis. There would be a horizontal asymptote there, just because as you keep raising half to higher and higher powers, it's going to become a 4th and an 8th and a 16th. It'll never become 0 though, so it'll just become smaller and smaller and approach that. So a real rough sketch here, but it will look something like this. All right, for number 28, let's check this one out. All right, in 28, we are depositing $2,000 into an account that pays 4% annual interest compounded continuously. What is the balance after 5 years? So while compound interest has its formula that we used back in the previous problem, here we have a continuously compound interest problem. So we have a slightly different formula if it's compounded nonstop or continuously. So the formula we're going to use here is A, which is the account balance again. That's going to be equal to P, the same thing we had earlier, that principal, what we start with, and that's going to be multiplied by E, that's a constant of about 2.71828. So e raised to the RT power, the R and T being the interest rate as a decimal, and T is time in years. Okay, so we are going to say the principal here is going to be $2,000. So I'm going to write P is equal to 2,000. And while we can totally just type in E into the calculator, just reminding you that it does have a value like pi, where it's a decimal that goes on forever. So 2.71828, those are just the first few decimals, but hopefully that kind of gives you a reference point for what it's roughly. And then we also have a few other things. We have the R, the interest rate. 4% as a decimal is going to be 0.04, okay? And then T is going to be time. We're talking about 5 years, so we're going to say T is 5 here. So let's go ahead and plug this in. The account balance after 5 years should be 2,000 multiplied by E raised to the RT power, which is going to be 0.04 multiplied by 5. All right, so let's see here. If we simplify this just a little bit, this is going to be 2,000 multiplied by E raised to the 0.2 power. We know this is going to be a growth function because E is greater than 1. It's 2.71828 roughly. Our starting value is $2,000. That's our y-intercept. And this is our exponent of 0.2 here. All right, plugging this into a calculator, we should get about $2,442.81. So after 5 years, if this $2,000 is compounded continuously at a 4% interest rate, it'll turn into about $2,442.81. Let's check out part 8 now, where we're going to look at some logarithmic functions together. For number 29, we have to go ahead and write the inverse for this function. So looks like we have an exponential function. We got to turn this into a logarithmic function, which would be its inverse. So first things first, when we're writing inverses, we take that f of x. Remember, that's just the same thing as y, right? So y is equal to 6 to the x power. Then when we have this, we're going to swap x and y. So instead of y equals, we're going to say x equals, and this is going to be 6 to the y power. Okay, so first step, turn f of x into y. Second step, swap the locations of x and y. And now we're going to solve for y. Now you need to know some logarithmic properties here, but if we have the base of this power on the right side as 6, then the inverse is going to be taking log base 6 of both sides. So I'm going to go ahead and write log base 6 of x on the left side of the equation. And on the right side, we're also going to write log base 6 of whatever's on the right side, which is going to be 6 to the y power. Okay, so one of the properties that we want to remember from logarithms as well is that if we have an exponent in a logarithm, we may bring it down in front here. So we can go ahead and say on the left side, we're going to still have this log base 6 of x. And on the right side, we're going to have y multiplied by this log base 6 of 6. Now, something else to kind of remember here is log base 6 of 6, this piece right over here, is just equal to 1. So if we know that this is equal to 1, then we can just say that y would be equal to log base 6 of x. So the inverse function here is going to be f of x is going to be equal to log base 6 of x. This would be the inverse function for that exponential function that we started with. Feel free to throw this on a graph to see what it looks like, but remember, inverses are really just graphs that are reflected across the line y is equal to x. So if you were to graph the exponential function that we had started with, it would look something along the lines of this, where it would be an exponential growth function looking something like this. And then if you graphed our logarithmic function, it would look something along the lines of this. So if you want to go ahead and graph that on Desmos or graphing calculator, feel free to do so. But these should be mirror images. I could probably draw that one a little better, but these should, if you reflect them across this diagonal line of y is equal to x, they should lie right on top of each other. Just a rough sketch. All right, for number 30, let's do another inverse here. This time we're given a logarithmic function. We have this ln, so this natural log instead of using a base of 6 in the last problem. So I'm going to go ahead and say this is going to be y equals, instead of writing f of x, and we have ln, and I'm just going to remind you that we have this e here, so I'm going to go ahead and write it in. It's implied that it's there, right, but I'm going to just write it in so it's extra clear, of this x plus 3 quantity. Okay, so first things first, we just kind of swap the f of x to y. I'm writing the e just to make this a little bit more clear, but after we turned it f of x into y, let's go ahead and just swap x and y's location. So we're going to say x is equal to ln of e. I'm going to keep that e down here just to make it super clear, and we're going to write y plus 3. Okay, so earlier we had an exponential function, so we used a logarithm to, kind of cancel out the exponential part so that we could be left with a logarithm. In this particular function, we're given a logarithmic function, so we're going to exponentiate to turn this into an exponential function. So again, we're using inverses to get rid of things here, or cancel things out. So the base here is e, so if we exponentiate the left side, we're going to just raise e, base of the power, to the x power. Okay, so it's e to the x on the left side. And if we exponentiate the left side, we're going to do the same thing on the right. So we're going to put a big E as the base, and the whole right side is going to become an exponent as well. So it's going to be ln of e, or ln base e rather, of this y plus 3. All right, so again, we knew to put these big e's here as a base of the powers because that was the base of the logarithm. Those are going to be inverse functions of each other. So on the left side here, we're going to see that this is going to be e to the x power is going to be equal to. Now on the right side, you're going to want to just remember that one of your properties of powers here and logarithms is that this is going to cancel out. So we're going to end up with this y plus 3 on the right side, just kind of simplifying that process down a little bit, but you can look at a video about that topic and more in particular if you want to know why that works. And if we just go ahead and subtract 3 from both sides, we're going to say y is equal to e to the x power minus 3, or say that our inverse function here is f of x is equal to e to the x power minus 3. This right here would be the inverse function for f of x is equal to ln of the quantity x plus 3. All right, check out number 31. Here it says sketch a graph of the function f of x is equal to log base 2 of x plus 3 plus 1. We're also going to go ahead and state the domain and range. All right, so first of all, I think it's going to be good to just look at what the parent function would look like here. So f of x is going to be equal to log base 2 of x. That would be the parent function. So we can go ahead and put a table together here so we can see what the values would look like and see what the graph would look like. All right, so we have a table here. Let's choose some nice values to plug in here for x. So maybe something like x would be equal to 2. If we have log base 2 of 2, that's just equal to 1. Maybe if x is going to be 4, log base 2 of 4 is just going to be equal to 2. Log base 2 of 8 is just going to be equal to 3. So those are all good values to do here. Then what if x is equal to 1? Well, log base 2 of 1 is equal to 0. And what if x is equal to a half? We can say if x is a half, then log base 2 of 1/2 would be negative 1. So just looking at the parent function, we would have some points we can go ahead and plot. So half comma negative 1 would be right about here. 1 comma 0 is going to be our x-intercept. 2 comma 1 over here in quadrant 1. 4 comma 2. And then 8 comma 3. So you can see here, this is our logarithmic function. Keep in mind that when we're dealing with logarithmic functions, we have these vertical asymptotes. So we're going to have something along the lines of this. In this case, it's not moving anywhere, so it's just going to be along the y-axis. Now, in terms of our graph, a rough sketch would look something like this. Again, this isn't even the graph of our actual function. This is just the parent function, so you can review a little bit about what the typical or parent functions for logarithmic ones look like. Now remember your transformations, this just means we're moving everything to the left 3 units. This is up 1 unit, so we have 2 translations here. So the x values need to be moved 3 units to the left. I'm going to go to write a minus 3, and the y values need to be moved up 1 unit. So if we go to move each of these y values and x values, I'm going to do the y values first. If this goes up 1, that's going to be at 0, up 1, that's going to be at 1, up 1, that's going to be at 2, up 1, that's going to be at 3, and up 1, that's going to be at 4. And then for our x values, if you go half and you go down 3, that's going to be at negative 2.5. If we're at 1 and we go down 3, that's going to be at negative 2. If we're at 2 and we go down 3, that's negative 1. 4 goes down 3, we're going to end up at 1. And 8 goes down 3, that's going to be at 5. So our new points here are going to be negative 2.5 comma 0. So I'm going to go ahead and plot that one over here. Negative 2 comma 1, which is right over here. Negative 1 comma 2 up here in quadrant 2, a little higher up. 1 comma 3 is going to be over here in quadrant 1. And then we have 5 comma 4. So I'll go over 5 and go up 4, something like this. Now because this whole function was translated 3 units to the left, hopefully it makes sense that our vertical asymptote is going to be 3 units to the left compared to where it used to be. And then we can see here that this will be the sketch of our logarithmic function with these 2 translations built in, where we have that 3 unit to the left and 1 unit up translation. This would be a rough sketch of this function. Now, as for the domain, keep in mind that this function doesn't go to the left and right forever. On the left side, it's going to be blocked off by the value of -3, where that vertical asymptote is. It will go to the right forever, so it'll approach positive infinity. Now, as for the range is going to be all real numbers. It's going to go down forever and up forever. Nothing is stopping it. It kind of makes sense that this is flipped of exponential functions. For exponential functions, the domain is all real numbers and the range is limited by the horizontal asymptote. So since logarithmic functions are the inverse of exponential functions, now we have a vertical asymptote instead. So you can see we have all real numbers for the range, but the domain is limited by that vertical asymptote. All right, cool. Let's check out one more here for number 32. It says, what are the solutions of this equation where we have log of 2x plus log of x minus 5 is equal to 2? All right, so we need to know some properties of logs to go ahead and do this. First thing I'm going to do is notice that we have the same base for these logarithms. They're both base 10, right? They're not writing it, but they're implied that they're base 10. If they're the same base, then we can condense this into one logarithmic expression. So we can write log base 10 of the quantity of this 2x multiplied by this x minus 5. So if we have addition between two logarithms that have the same base, you can condense it using a product. And so that's what I just did right here. Okay. What we can then do is we can rewrite this into exponential form if you'd like, or we can go ahead and exponentiate to get rid of the logarithm, whatever you want to do to kind of write that out. Maybe what I'll do is just write that this is base 10 here. And maybe I'll just write the exponentiation of it. So if the base is 10 of the logarithm, the inverse is exponentiating. So I'm going to write a 10 raised to the log base 10. This whole thing on the left side becomes a little exponent here. So log base 10 of 2x times x minus 5 is equal to, and on the right side we should exponentiate as well using the same base of 10. And again, we're using 10 because that was the base of the logarithm. We said earlier that this just kind of cancels out. I'm not going to go into the specifics right now, right? But on the left side, we're going to be left with, and I'm going to actually distribute here so that we don't have to do it later. 2x times x is going to be 2x squared. 2x times -5 is going to be -10x. And on the right side, 10 squared is going to be 100. So notice how we turned this logarithmic equation into just a standard quadratic equation. I'm going to go ahead and just divide everything by 2. So we have x squared minus 5x is equal to 50, and move everything to the left side by subtracting 50. So x squared minus 5x minus 50 is equal to 0. I'm going to go ahead and choose to factor here because I think this works out nicely. I think it's going to be x minus 10 and x plus 5. And if we use the zero product property to make each of these binomials equal to 0, x could be 10 or x could be -5. Those would be two solutions here. All right, so we got these two solutions, but we should always check for extraneous solutions as well. If we go ahead and take this x equals 10 and plug it in here and here, let's see if this works out. So if we did that, we'd be testing and saying it would be log of 2 times 10, which is 20, plus log of, let's see, 10 minus 5 is going to be 5. So it's going to be log of 5. Is that equal to 2? Well, if we go ahead and condense this, this would be log of, and you can multiply 20 times 5. That'd be log of 100. Is that equal to 2? Well, let's see. Keep in mind that there is this base of 10 here down here. So is if we rewrite this in exponential form, is 10 to the second power equal to 100? And that is, so this is true. So this would be one of our solutions. So this does work. So we know 10 x equals 10. Okay. Now, what about our other one? Well, let's take a look and see if you plug in this -5 into this, you have this negative value here, which isn't going to work if you look at the domain and range of this function. So if you go ahead and plug in -5 in either one of these, keep in mind we can't take log of our negative numbers, right? So x equals -5, while we did get it algebraically, it's an extraneous solution. In part 9, let's take a look at some trigonometry together. So in 33, let's go ahead and write the multiples of 30 degrees and 45 degrees up until 360 degrees in radians together. So let's go ahead. Actually, I'm going to start with 360 instead. So 360 degrees is the same thing as 2 pi. So I think it's a good starting point here, okay? So I'm going to go ahead and break it down from here and then get smaller and smaller, but I'll fill in the blanks as we go. So I like starting with 360 and just saying, well, 180 must be the same thing as pi because that's half of each of those, okay? But also half of that is going to be 90 degrees. So 90 degrees, half of a pi would just be pi over 2, or half of a pi, right? And then 45 degrees is going to be half of that. So half of a half is going to be a quarter. So I think these are good ones to kind of have right off the bat. Then what about coming up with 30 degrees? Well, if we take this 180 degrees right over here and we divide that by 6, then we would end up with 30 degrees, right? So 30 degrees here would end up being pi divided by 6. So we have to write all the multiples, I guess, of this 30 degrees, which is going to be right over here, which is, we have this as pi over 6. And we also have this 45 degrees, which is this pi over 4. So we're going to go ahead and write the multiples of these in radians. So for multiples of 30 degrees, the first one is going to be 30 degrees or pi over 6 in radians. After that, we're going to add on another 30 degrees or another pi over 6. That's going to be 2 pi over 6, which is the same thing as pi over 3 if we simplify it. Then we're going to have 3 pi over 6, but that simplifies down to pi over 2. Okay, that's the same thing as 90 degrees, which is a multiple of 30 degrees. Then after 3 pi over 6, we have 4 pi over 6, but that simplifies down to 2 pi over 3. That's 120 degrees, right? And then if for 150 degrees, instead of 4 pi over 6, we're going to have 5 pi over 6. This one's not going to be able to simplify here. That's 150 degrees. And then we're going to have 6 pi over 6, or that's going to be the same thing as pi. So that's right there. The sixth multiple here is going to be 180, which makes sense because 30 times 6 is 180. For 210, we're going to go ahead and add another pi over 6. So it's going to be 7 pi over 6. That's 210 degrees. Then we're going to have 8 pi over 6, but that simplifies down to 4 pi over 3. Alrighty. And then we're going to have, after 8 pi over 6, we're going to have 9 pi over 6, which simplifies down to 3 pi over 2. Same thing as 270 degrees. And then after 9 pi over 6, we have 10 pi over 6, which simplifies down to 5 pi over 3. That's going to be 300 degrees. Okay. If we had 10 pi over 6 there, the next one's going to be 11 pi over 6. That's the same thing as 330 degrees. And then finally, we have 12 pi over 6, which simplifies down to 2 pi, and that's 360 degrees. So notice here, how many multiples do we have? Well, we have 30, 60, 90, 120, 150, 180. Then we have 210, 240, 270, 300, 330, and 360. So these are the first 12 multiples up to 360. All right, now for 45 degrees, we should have less of these. 45 degrees is the same thing as pi over 4. Now, if we add another pi over 4 onto that, it's going to be 2 pi over 4, which is really just pi over 2, or 90 degrees. If we add another pi over 4 to that 2 pi over 4, that's going to be 3 pi over 4. So what's 90 plus 45? That's 135 degrees, right? And then if we add another pi over 4, that's going to be 4 pi over 4, or the same thing as pi. So that's 180 degrees. All right. After that, if we add another pi over 4 onto that, that's going to be 5 pi over 4. So that's the same thing as 180 plus 45, or 225 degrees. If we add another pi over 4, that's going to be 6 pi over 4, but that simplifies down to 3 pi over 2. That's the same thing as 270 degrees. And then if we had 6 pi over 4, we add another pi over 4, that's going to be 7 pi over 4. Okay, that's the same thing as our 270 plus 45, that's 315. Add another 45 degrees onto that, or another pi over 4, that's 8 pi over 4. That simplifies down to just 2 pi. All right, so here's 45 degrees, 90 degrees, 135, 180, 225, 270, 315, and 360. These are all the multiples of 45 degrees up to 360. All right, let's check out number 34. For 34, without a calculator, we're going to go ahead and determine the value of secant of 11 pi over 6. So for starters, I like to just look at the angle measure here. So we have 11 pi over 6. So let's kind of think about where that's going to be. So 11 pi over 6, if we go ahead and convert that into degrees, just so we can visualize what this is going to be, if degrees are easier for you, we can multiply this by 180 over pi, which is really just 1 over 1. If we go ahead and cross cancel here, the pi's will cancel out. The 6 and 180 will cross cancel as well and become 1 and 30. So 11 times 30 here is going to be 330. So this is the same thing as 330 degrees, just to help you visualize it. Maybe you already knew that from just looking at 11 pi over 6. But it's helpful to know that so we can visualize where this is. If this is going to be 0 degrees right over here, then 330. Again, we're going to go this counterclockwise. We're going to end up somewhere here in quadrant 4, right? So 330 degrees is going to be 30 degrees away from 360, or a full circle here. So this is going to be the terminal side. But we're seeing where we started from 0 degrees all the way around here. this is where the 330 degrees is going to end up. So what's our reference angle here? That means our reference angle here is going to be 30 degrees. And if we want to, we can take a look at a right triangle over here in quadrant 4 based on that. So let's go ahead and take a look at this right triangle a little bit more clearly over here. So we know this is going to be 30 degrees. If we have a 90-degree angle there, then this other angle must be 60 degrees. So this must be a 30, 60, 90 triangle. Now remember that for a 30, 60, 90 triangle, we have specific ratios of their side lengths for all of them, right? They're just going to be similar right triangles. So for 30, 60, 90 triangles, we always have 1 for the shortest length. We are always going to have 2 for the longest length. We're going to have the square root of 3 for the middle length there. So they're always going to be in this ratio of 1 to root 3 to 2 from the shortest side to the longest side for a 30, 60, 90 triangle. Also keep in mind, because we are in quadrant 4 here, this is an x value. So again, if we're plotting the point over here, this is going to be going in the right direction or positive. We're going down here, so this must be actually a -1. Now the other thing we want to talk about real quick is the secant function here. So keep in mind that if we have secant of theta, that's actually a reciprocal function. Secant is the reciprocal of cosine, right? So it's really just the same thing as 1 over cosine of theta. That being said, if we multiply both sides of this equation by cosine of theta and divide both sides by secant of theta, we could say that cosine of theta would be the same thing as 1 divided by secant of theta. Basically, whatever we find out for cosine of theta, we can just find the reciprocal of it, and then we'll have secant of theta. So what do we have in this particular problem? Well, this is the angle we're dealing with. It's 30 degrees, right? So let's go ahead and find cosine of this 30 degrees. I'm going to go ahead and write it just like this, keep those colors consistent. So cosine of theta, think about cosine, I'll go ahead and write this on the side here, but cosine, the ratio is going to be adjacent over hypotenuse if you use SOHCAHTOA, or you can say that cosine is going to be always the x value over the r value, okay, or the ratio of the horizontal distance to the radius of that unit circle. In this case, our radius here would be 2, I guess, though, right? Just another similar triangle. So our x value here, or our adjacent side, is going to be positive root 3 over 2. Our hypotenuse here is going to be 2, and that's always going to be positive. We're looking at that hypotenuse or the radius there. So I'm going to go ahead and write this as positive root 3 over a positive 2. All right, so we know cosine of 30 degrees is this root 3 over 2, but we want to find what secant of theta is. So that's really just going to be 1 divided by whatever cosine of theta is. So if we want to go ahead and write this, we can say secant of this 30 degrees is going to end up being 1 divided by this root 3 over 2. So you can just flip it upside down. I'm just being very detailed with this. So if you divide, you're going to multiply by the reciprocal. So it's going to be 1 times 2 over root 3. And that's just going to equal 2 over root 3. Now keep in mind, we're going to rationalize the denominator, so we're going to multiply top and bottom by root 3 over root 3. So we can say that secant of 30 degrees is going to be 2 root 3 over 3. And so, while 30 degrees was our reference angle, it was really just helping us understand that we were dealing with this 11 pi over 6, or 330 degrees, and the secant of that 11 pi over 6 is this 2 root 3 over 3. Let's check out number 35. In 35, we have point Q, which is at -5, 12. It's a point on the terminal side of theta in standard form. Find the exact values of the trigonometric functions of theta. Okay, so let's go ahead and visualize what this is looking like first. All right, if we're looking at a coordinate plane here, this -5, 12 has got to be somewhere in quadrant 2, right? So it's going to be up here somewhere, 5 to the left and 12 units up. So I'm going to go ahead and actually draw a right triangle here. So this is going to be 5 units to the left. So I'm going to write -5 this way. Okay, and then I'm actually going to go 12 units up, which is going to be right over here. That's going to be positive 12. So once we have the x value and that y value, we can go ahead and connect this to make a right triangle. And if we have a right triangle and we're interested in how long this segment is over here, we can go ahead and use the Pythagorean theorem. So we can say a squared, which is going to be this -5 squared, plus the b squared, which is going to be 12 squared. That's going to be equal to the hypotenuse squared. I'm going to call that c here. We can call it whatever variable you want. -5 squared is 25, 12 squared is 144, and then we have that's equal to c squared. Summing those, we're going to get 169 is equal to c squared, and taking the square root of both sides, we're going to find out that the hypotenuse here is going to be 13. So that's going to be this measurement here. And so we really need to know that value before we can do anything else. So what are the 6 trig functions again? Well, we have this sine of theta in this case, and theta is right over here. We have cosine of theta, and then we have tangent of theta. Those are our main 3. Then we have our reciprocal functions. So our reciprocal functions, we have cosecant of theta, then we're going to have secant of theta, and then we're going to have cotangent of theta. Okay, so sine of theta is going to be, I'm going to go ahead and just write this down to help you remember maybe, but sine is always the y value over the r value, cosine is always the x value over the r value, and tangent is always going to be the y value over the x value. And then our cosecant of theta and secant of theta and cotangent of theta, these 3 over here are just going to be the reciprocals of these 3 over here. So I'm not going to write those down. So let's do sine over here first. So it's y over r. So y is the up and down value. So it's 12. And then this is the radius or the hypotenuse, so it's going to be 12 over 13. Let's go ahead and write 12 over 13. Then if we go ahead and write cosecant of theta, keep in mind it's 1 divided by that, or just the reciprocal. Then we have cosine of theta. Cosine is going to be x over r. Here's our x value. It's negative 5 over this 13. So it's going to be negative 5 over 13. And so for secant of theta, it's going to be negative 13 over 5, right? Just the reciprocal. And then finally, we have tangent of this theta. Tangent is going to be the y value over the x value. So here's the y value. It's going to be 12. And the x value is negative 5. So we're going to have negative 12 over 5, right? A negative divided by a positive, or positive divided by negative is going to be negative. And for a cotangent of theta, it's going to be negative 5 over 12. All right, let's check out number 36. And here we're given that tangent of theta is equal to negative 3/4. We're going to go ahead and determine all 6 trigonometric ratios and the value of theta. All right, so let's start by looking at the original equation. We see that tangent of theta is equal to negative 3/4. Now, if we want to go ahead and figure out what theta is, we could do a number of things, but what I'm going to do is just use the inverse tan function. So I'm going to go ahead and take arctangent or inverse tangent of the tangent of theta on the left side. And on the right side, I'm also going to take arctangent or inverse tangent of that ratio of negative 3/4. Okay, so on the left side of the equation here, these are inverses, so we're just going to go ahead and cancel this out and have theta here on the left side. And then if we go ahead and plug in this inverse tangent of negative 3/4, depending on if you're doing this in radians or degrees, you're going to get a different value, but I'm going to go ahead and do this in degrees, and it's going to be approximate, so I'm going to go ahead and use an approximation symbol here. This is going to be theta is approximately negative 36.87 degrees. Okay, and see if that makes sense here. So what I mean by that is if we knew tangent of theta is negative 3/4, remember that tangent's ratio is going to be y over x, right? Now we do have a negative value here, so we know that tangent's, this reference angle or triangle we can draw, it can't be in quadrant 1 because that would be any positive value over positive value for any point over here in quadrant 1. And again, we have a negative ratio here. It also can't be over here in quadrant 3 just because we would have a negative value over negative value, right? All the y values here are negative, all the x values here are negative, so negative over negative would be positive. Then you might be thinking, okay, it could be in quadrant 2 or it could be in quadrant 4, but the range of the arctangent function is restrained to negative pi over 2 to positive pi over 2. So that means that we have to be able to draw this triangle. We know this angle has to be in quadrant 4, and this go ahead and confirms it because we have this negative angle. So if this is 0 degrees right here, then negative 36.87 roughly would be somewhere over here. This is that negative angle. All right, so again, our ratio here is going to be this negative 3/4. So this must be our y value. This is going to be our x value. I'm going to go ahead and rewrite this as going to be negative 3 over positive 4, just so you can see that that is what we're going to be doing. So if we go ahead and say the y value is negative 3, but the x value is positive 4, that would look something like over here. And I can show you here that this is going to be that positive 4 to the right, and this is going to be that negative 3 down. Okay, so if we want to go ahead and figure out what this value is over here, the hypotenuse, you can go ahead and use Pythagorean theorem here, but hopefully you also notice it's a 3, 4, 5 right triangle, so that makes the hypotenuse a little bit easier to figure out here. All right, so our theta is right over here. We know it's about negative 36.87 degrees, but now that we have all three sides of this right triangle, we can write all 6 of our trig functions, our ratios for it, right? So we have sine of theta. In this case, we know the angle, but I'm just gonna write sine of theta. I'm gonna go ahead and write cosine of theta, tangent of theta. Tangent of theta, we actually already know. I'm going to just write it already. It's going to be negative 3/4. Again, that's going to be the opposite over adjacent, or we can say the y over x value. Then we have our reciprocal trig function. So we have cosecant of theta, then we have secant of theta, and then we have cotangent of theta. All right, so for cotangent, I'm going to do that one right away because it's just a reciprocal of negative 3/4. That's going to be negative 4/3. Now for cosine, let's see, cosine is going to be its x value over the r value. So this is going to be 4/5. So I think that's going to be cosine of theta. And so secant of theta is going to be 5/4. Okay. And then for sine of theta is going to be the y value over the r value. So the y value is negative 3. The r value or the hypotenuse here is 5. So I'm going to say it's going to be negative 3/5. So cosecant of theta is going to be negative 5/3, just the reciprocal. Also keep in mind that for theta, you can also think about this as instead of negative 36.87, if you go ahead and add on 360 to that, you're going to get about 323.13 degrees. That's just a coterminal angle here, right? So if you add 360s in the same location, you might want to go ahead and use that angle if you're just checking anything out here, just so we're fitting the domains and ranges for the other trig functions as well. For this last section, let's take a look at part 10, which is going to be dealing with some trigonometric functions. For number 37, let's go ahead and sketch the graph of f of x is equal to negative 3 times cosine of this 2 pi x plus 4 pi. So keep in mind that one way to look at these trig functions is to put them in this form so that we can identify our a, b, c, and d values. So rewriting our function here, we can just go ahead and say that this a value is going to be negative 3. Our cosine function is just going to stay the same here. Now if we go ahead and rewrite this so that we have this x by itself here, let's go ahead and factor out this 2 pi. So I'm going to factor out 2 pi in front here. If I factor out 2 pi, they're going to be left with x. And then we're going to go ahead and take away c. Now in this case, c is going to be negative 2. So we're going to take away a negative 2 here just because we have a plus 4 pi. So it's minus minus. All right, so it's going to look something like this. And then we're going to go ahead and add d on the outside. In this case, we're not adding anything, so d is going to be 0. If you want to check this real quick, you can go ahead and distribute 2 pi times x. You're going to get 2 pi x. This x minus minus 2 is really just x plus 2. So 2 pi times that 2 is going to be this 4 pi here. So we can see that a is going to be negative 3, b is this 2 pi, c is going to be negative 2, and d is going to be 0. All right, now keep in mind, if you're trying to visualize what the typical parent function for cosine functions looks like, it's going to start up here at 0, 1, it's going to come down, it's going to come back up, it's going to look something like that for one period. It's also important to remember that when we're looking at the parent function, we typically are looking at these values of x is 0, then we have x is pi over 2, which is 90 degrees, then we have pi or 180 degrees, 3 pi over 2, which is 270 degrees, and then 2 pi. So that would be one full cycle of the unit circle, right? And for this parent function, we can see here that the y value is going to be at 1, then it's going to be at 0, then negative 1, then 0, then positive 1. So it's important to know the parent function here for this f of x is equal to cosine of x. Now, while this is the table for the parent function, we have to figure out the table for the actual function we are given in this problem. And that's actually going to be where this a, b, c, and d come into play. So using those a, b, c, and d values, we're going to take each of our x values here and multiply them each by 1 over whatever b is. And then we're going to go ahead and add on whatever c is afterwards. Now for our y values, what we're going to do is multiply each of them by whatever our a value is. And then we're going to go ahead and add on whatever our d value is. So b and c are going to go together and a and d are going to go together. Let's go ahead and take this x equals 0 first, multiply it by 1 over 2 pi. So 0 times 1 over 2 pi. And then take away 2, that's going to be 0 minus 2, which is going to be negative 2. Next, take this x is pi over 2, and let's go ahead and multiply that by 1 over b. 1 over b is going to be 1 over 2 pi, and let's go ahead and take away 2 afterwards. So these pi's will cross cancel. We're going to be ending up with 1/4 minus 2, which is going to be -1 3/4, which is the same thing as -7/4. So I'm going to write -7/4. That's going to be this new x value. Then when x is pi, let's take this pi over 1 and multiply it by 1/b, or 1/2 pi, and then take away 2. These pi's will cross cancel, so we're going to end up with 1/2 minus 2, which is going to be -1.5, and that's the same thing as -3/2. Next, x is going to be 3 pi over 2, so let's go ahead and take 3 pi over 2, multiply by 1/b, or 1/2 pi, then take away 2. These pi's will cross cancel, so we're going to end up with 3/4 minus 2, so that's going to be 3/4 minus 8/4, which is -5/4. Go ahead and put that right over here. Finally, we have 2 pi over here, so let's take this 2 pi and write that over 1, multiply by 1/2 pi, then take away 2. These 2 pi's will cross cancel, so you're just left with 1 minus 2, and that's going to be -1. For our new y values, let's see, we have y is equal to 1. Let's go ahead and multiply 1 by whatever a is. A is -3, so 1 times this -3. Then add d, which is 0, so 1 times -3 is -3 plus 0, which is still going to be -3. Now y is going to be 0. Let's take the 0 and multiply that by a, which is -3. Let's go ahead and then add on d, which is 0, so 0 plus 0 is going to equal 0. Put that right here. Now x is, let's see, x is going to be -1 here, so it's going to be -1 multiplied by this a value of -3, plus d, which is 0, so it's going to be 3 plus 0, which is 3. Now we see y is equal to 0. Let's go ahead and take the 0, multiply it by a. A is -3. Let's go ahead and add on d, or you can see that's going to be the same thing as when x was pi over 2. So this is still going to be 0. And then you can see for this last one, when y is 1, that should match when y is 1 here. So however you want to do this is fine, but we're going to end up with -3 again. All right, so what is this sketch going to look like as a graph? So plotting -2, -3, that's going to be over here. -1 3/4, comma 0 is going to be right here on the x-axis. Plotting -3 over 2, comma 3 is going to be right over here. Then -5 over 4, comma 0 is back along the x-axis. Then -1, -3 is down here below the x-axis. So making a rough sketch, we should try to draw a somewhat smooth curve here. It looks something along the lines of this. Okay. Hopefully this makes sense, just because normally if you look at the parent function, it starts up top here, then it drops down, then it comes back up. In this case, we're seeing that we're starting down here, and we're kind of doing the flipped version of this vertically. So we're starting at the bottom, going up and coming back down. This hopefully makes sense because our a value is -3, so it's flipping everything upside down vertically. Also, we have a vertical stretch, so the parent function usually has an amplitude of 1. So it goes up to +1, down to -1, but now we go up to +3 and down to -3. So that's what that -3 does. And you can see all the other different transformations here. This whole thing moved to the left 2 units, and also you can see there's this horizontal compression that happened as well. So here's a rough sketch. And of course, you can continue this pattern if you'd like to see what more of these periods would look like, roughly something like this, right? But I just drew one period here. All right, here is number 38. In 38, let's go ahead and solve this triangle ABC. We know that one of the side lengths is going to be A is 11, side length is C is 14, and an angle measure is B is 34 degrees. All right, so maybe here is a rough sketch. I'm going to go ahead and say this is going to be angle A. I'm going to call this my angle B and call this angle C. Doesn't really matter, just see where you want to put your pieces here. If side A is going to be opposite of angle A, then this has to be 11 over here. Side C has to be 14, which is going to be down here, and then angle B is 34 degrees, so I'm going to put that right over here. So it's included between those two sides. Notice here how you have a side, you also have an angle, and you have a side. So we have this SAS. So this is a pretty classic example of when you would use law of cosines to help you solve this triangle to begin. Now keep in mind that when they say we're going to solve this triangle, that means that we're going to be figuring out all 3 angles and all 3 sides. So let's just take into consideration what we have already. We know B is going to be 34 degrees, so that one's taken care of. We also know side A is going to be 11 and side C is going to be 14. So it looks like we actually have 3 of these pieces. We're just looking for the other 3. To help us along with that, we have this law of cosines formula we can use. Again, there's 3 versions of this depending on what you're looking for, but this is going to hopefully help us out because we know the angle measure B is going to be 34 degrees. So I'm going to use the formula here that has cosine of B in here. So plugging this in, we don't know B, so it's going to be B squared. That's going to be equal to C squared. C squared is going to be what? 14 to the second power. Plus a squared. A is going to be 11 squared to the second power minus 2 times a, which is 11, times c, which is 14. I'm going to multiply this by cosine of 34 degrees. Now, if we go ahead and plug in the entire right side of this into a calculator, we can find out that b squared is going to be roughly 61.66. And if you take the square root of both sides here, we're going to get the value of b is going to be about 7.85. Okay, so roughly the side length of b is going to be about 7.9. Go ahead and write that right over here as well. Now, to figure out angle measures a and c, I'm actually going to go ahead and use law of sines instead. We can say that the ratio of side length a to sine of angle a is going to be the same as the ratio of side length b over sine of b. So if we go ahead and plug in some values here, we can find out, let's see what a is going to be. A is 11, right? And then for sine of a, we don't know what that's going to be. So sine of a, angle measure a. B is going to be, we said, about 7.9. And we also know that sine of b, let's see, we can write sine of 34 degrees. Okay, so we can go ahead and use some cross products here, and we can say that the product here is going to be equal to the product over here. So we can say that 7.9 multiplied by sine of a is going to be equal to 11 multiplied by sine of 34 degrees. Dividing both sides by 7.9, we can say sine of angle A is going to be 11 multiplied by sine of 34 all over 7.9. And then if we take the inverse sine of both sides here, we'll see that angle A is about 51.13 degrees. So I'm going to just put that up here as 51.1 degrees roughly. Just filling this into our triangle, I'm just going to see where we are having all our pieces filled in. And then for this last angle measure C, all we have to do here is take 180 and take away 34 and take away 51.1. So I'm going to go ahead and write that angle C is going to be 180 minus the 34 degrees minus the 51.1 degrees. So we're going to get C is going to be roughly, because we did some rounding earlier, going to get about 94.9 degrees. So that's going to be our angle C. Let's go ahead and put that right in our triangle here and then move on to number 39. All right, in 39, let's go ahead and sketch the following function of f of x is negative 2 times sine of 2/3 times the quantity of x minus pi over 2. And let's go ahead and state the domain and range. All right, so similar to our function earlier with the cosine graph, let's go ahead and use the same format for our sine graph here. Using this outline, we can go ahead and say that f of x is going to be equal to a. In this case, a is going to be negative 2, so we have a vertical stretch as well as a reflection across the x-axis, or vertical reflection here, multiplied by sine of what? Well, we have a b value, it looks like, of 2/3. That's going to be our b value multiplied by the quantity of x, and then it's going to be minus c. Looks like c is just going to be positive pi over 2, so that's going to be moving this graph left and right a little bit here. And then we're going to go ahead and add d here. In this case, d is also going to be 0 like in number 37 as well. So there's no vertical translation at all. So let's go ahead and use the fact that we know a, b, c, and d to go ahead and figure out what this graph is going to look like. All right, remember, just a reminder what the parent function for the sine graph looks like. It's going to look something like this, where it starts at the origin. It's going to come up, then come back down, then come back to the x-axis. Now remember, what does that parent function look like for the sine function? Keep in mind that's going to be coming from the origin, coming up, then coming down, then coming back to the x-axis. So that's what the parent function is generally looking like. And for a typical unit circle, this is going to stay the same for 0 degrees, 90 degrees, 180, 270, and 360. But what are the y values going to be? Well, starting at the origin, so it's going to be at 0, 0. Then it's going to go up to 1, back to 0, down to -1, and back to 0. Now let's go ahead and use our a, b, c, and d values to figure out what our new table is going to be for this particular function. So let's go ahead and take each of our x values, and let's see what we did earlier. We multiplied each of these x values by 1 over b, then we went ahead and added c on afterwards. And then for each of our y values, we're going to multiply each of them by a, and then add on d afterwards. If we take the 0 here and multiply by 1 over b, 1 over b is going to be 1 over 2/3, which is really just going to be the reciprocal, so it's going to be 3 over 2. And then add on c, looks like c is going to be pi over 2. So that's going to be a total of pi over 2. So let's go ahead and put that in here. That's going to be our new x value for that first spot. I'm going to go ahead and do the y values that correspond with each one right now. So I'm going to take this 0 here, let's multiply by a. A is -2, right? It's right over here. And then we're going to go ahead and add on d, which is 0. So this is just going to be 0. For when x is pi over 2, let's go ahead and take pi over 2 here. We're going to multiply by 1 over b, so 1 over 2/3 again is going to be 3 over 2. Then add on c, which is going to be pi over 2. So let's see, if we go ahead and multiply this out, this is going to be 3 pi over 4 plus pi over 2, which is the same thing as 2 pi over 4. So I think this is going to be 5 pi over 4. Let's go ahead and put that in here, 5 pi over 4. Now, what's the y value that goes with that? Well, this y value is 1. Let's go ahead and multiply it by a. A is -2, and go ahead and add on d afterwards. So 1 times -2 is -2 plus 0, so it's still going to be at -2. For when x is pi, let's go ahead and take this pi and let's write pi over 1. Let's multiply by 1 over b, which is going to be times 3 over 2. Then add on c, which is going to be pi over 2. So this is going to be 3 pi over 2 plus pi over 2, which is 4 pi over 2, which is really just 2 pi. So let's go ahead and put 2 pi over here. And for when y is equal to 0, notice that we had y equals 0 here. So when this is 0, this is also going to be 0. So I'm just going ahead and write that in. Now what about when x is 3 pi over 2? Let's take this 3 pi over 2, multiply it by 1 over b, or times 3 over 2, then add on this pi over 2. So let's see, this is going to be 9 pi over 4 plus, and then we can say this is going to be 2 pi over 4. So that's going to be a total of 11 pi over 4. So I'm going to put that x value in here, 11 pi over 4. Now when y is equal to -1, let's take this -1, multiply by a, which is -2, then add on 0. So this is just going to equal 2. And then finally, when x is going to be 2 pi, let's take this 2 pi over 1, multiply by 1 over b, or times 3 over 2, then add on this pi over 2. We can cross cancel here, so this is going to be a total of 3 pi plus this pi over 2. So I think that's going to be 7 pi over 2. Go ahead and write that in here. It's going to be 7 pi over 2. And notice here we had these y values that were all the same, so our y values here are all going to be the same as well. All right, so we have our table now. And if we go ahead and graph one period of this function, pi over 2 comma 0 is here. 5 pi over 4, which is 1 1/4 pi, and then -2, so it's going to be somewhere down here, right? And then 2 pi comma 0 is going to be right at the x-axis. 11 pi over 4, it's the same thing as 2 3/4 pi, so it's going to be closer to 3 pi, and it's going to be up here at +2. And then 7 pi over 2, which is 3.5, so 3.5 pi comma 0 is going to be over here along the x-axis. So we try to make a smooth curve here. It's going to come down first, right? And then it's going to come back up, and then it's going to come back down. So this would be one period of this function. Now keep in mind, for the parent function for sine, it went up, then down, then up back into the x-axis. So in this case, it's going down, then up, then down, just because we had a value that was negative, so it's flipping it upside down. For the domain of this function, we can go ahead and say this is going to go from -infinity to +infinity, because it's going to keep going from left to right. Now, as for the range of this function, the lowest point this graph will go to is -2 because of the amplitude, and also the highest point it'll go to, or highest y value, or the maximum will be at +2. Keep in mind you want to put brackets on these numbers because the function does hit these values. All right, here's one final problem for this review on Algebra 2. For number 40, we're going to go ahead and verify a trigonometric identity. So we're going to try and prove that this left side is the same as the right, or the right side is indeed the same as the left. So here we have secant of x plus tangent of x must be equal to cosine of x over 1 minus sine of x. Now what I'm going to do here is I'm going to go ahead and see if I can make this right side look like the left side. So let's go ahead and take this cosine of x and put this on top of this 1 minus sine of x and see if we can use some of our trigonometric properties and identities to see if we can rewrite this as the left side here. Now, on the bottom here, this 1 minus sine of x, this looks a little suspicious to me. I think what we're going to do is use the conjugate here and multiply this by 1 plus sine of x. You're going to hopefully see this in just a moment. So I'm thinking of a trig identity, and if you have a sheet you can take a look at, that might be helpful so you can see. But I'm using this difference of squares pattern here. It's 1 minus this and 1 plus this, the same type of term here, and you're going to see what's going to happen. So if you look at the numerator, I'm just going to keep this a little bit separate. I'm going to say it's going to be cosine of x multiplied by the quantity of 1 plus sine of x. And let's see, the bottom is going to be this 1 minus sine of x multiplied by this quantity of 1 plus sine of x. So if you kind of remember back from quadratics, if you have something like this where it's a minus b times a plus b, then that's always going to turn into a squared minus b squared, right? Because if you FOIL it out, the outers and the inners will cancel each other out. So I'm going to use that pattern here as well. So if we look at the top here, the top is going to be cosine of x. I'm just going to leave that alone, times this 1 plus sine of x. But what's going to happen to the denominator here that's going to be nice is if we FOIL this out, it's going to be 1, and then the outers and the inners are going to cancel out, and it's going to be minus sine squared of x. So it's going to have 1 minus sine squared of x. All right, now this 1 minus sine squared of x is the same thing as cosine squared of x. So that's one of our trigonometric Pythagorean identities. So I'm going to go ahead and say, we can say this is cosine of x times this 1 plus sine of x. And that's again going to be on top of this cosine squared of x. So if you want to pause and look up that Pythagorean trig identity, feel free to do so. Next, we can see here that we have a common factor of cosine of x on the top and bottom. So we can go ahead and cancel out this cosine x with one of the cosine x's that's being multiplied on the bottom. If we go ahead and do that, we're just going to be left with 1 plus sine of x over cosine of x, because just keep in mind this cosine squared of x is really cosine of x times cosine of x. So I just canceled out one of each of those. All right, now let's go ahead and separate this into two different fractions. So it's going to be 1 over cosine of x plus sine of x over cosine of x, right? At the end of the day, we're trying to get two different trig functions being added together here. Now, keep in mind, what is this 1 over cosine of x? Well, that's the reciprocal of this, cosine rather is the reciprocal of secant, so 1 over cosine, or the reciprocal, should be just secant of x, right? So we can go ahead and say that that's going to be secant of x. So I'll just try to make that a little bit more clear, that this right here is the same as this. Okay, and then another identity you'd want to just kind of remember is if you look at this sine of x over cosine of x, that's the same thing as tangent of x, which is right over here. So we can go ahead and write plus tangent of x. So that's what this turns into. So you can see here that the secant of x plus tangent of x was what we had on the left side of the equation to start. So we went ahead and used some of our trig properties and identities to go ahead and prove that these were identical to each other. All right, so that just about wraps up this video on 40 different practice problems spanning across Algebra 2. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.